Now, if Earth were the size of a nickel, Neptune would be about as big as a baseball. That's impressive, but it's nothing compared to the giant ninth planet that might be hiding out there. Now, our Planet 9's discovery saga might have finally come to an end. Turns out, the problem wasn't where we were looking, but how. And researchers might have just made the biggest solar system discovery in decades. You see, the idea of finding a planet beyond Neptune has been around for years now. I know, back in school, you probably learned that the ninth planet was Pluto. But forget about Pluto. It's been demoted to a less fancy category since 2006. What I'm talking about is the Planet 9, a hypothetical giant planet that could be our cosmic neighbor. We've never actually seen it, but scientists are pretty sure it's out there somewhere, hiding in the outer solar system. To explain why they think that, we need a sheet of paper. Hey, here's one. We place a coin on it, and suddenly, it starts to move. Unless we're talking about some kind of superpower, there's no way this coin is moving on its own, right? So, you figure someone must be on the other side, holding a magnet and moving it around. You can't see the magnet, but it explains why the coin is moving. That's kind of what's happening with Planet 9. We can't see it, we can't prove it, yet, but its existence could explain the strange movements we see out there in space. For example, the planets in our solar system orbit on a flat plane that's tilted about 6 degrees relative to the Sun. But why 6 degrees? Well, no one really knows for sure. Some scientists think those orbits might be slightly tilted because of the pull of a ninth planet. Its existence could also explain the unusual paths of smaller objects in the distant Kuiper Belt, a region full of icy debris that stretches far beyond Neptune's orbit. Back in 2016, researchers from Caltech published a study about Planet 9. They suggested it could have a mass about 10 times that of Earth and follow a highly elongated path. It's a scientific way of saying it takes forever to make one trip around the Sun. Because of that, it would be located in the outer solar system, far, far away. It would orbit the Sun about 20 to 30 times farther out than our most distant planet, Neptune. According to scientists, Planet 9 would take up to 20,000 Earth years to complete just one full orbit around the Sun. Since it's crazy far out there, it's almost impossible to see it. So, as cool as this hypothesis sounds, we've never found solid evidence that Planet 9 actually exists. But we might be pretty close. In May 2025, a team at National Tsinghua University might have made one of the most exciting solar system discoveries ever. Alright, so there's a hypothesis that Planet 9 hasn't been discovered yet because we haven't been using the right method. This new study raises an interesting question. What if Planet 9 actually looks brighter in infrared light than it does in visible light? Let me explain. Scientists have been trying to spot Planet 9 by its reflected light. But here's the problem. To spot it in visible wavelengths, sunlight would have to travel all the way out to Planet 9, bounce off its surface, and then travel all the way back to Earth. If a Neptune-sized planet were about 10 times farther away than Neptune, it would look about 10,000 times fainter. But a planet's own thermal radiation, its heat, only has to make a one-way trip. So in infrared light, Planet 9 would only be about 100 times fainter. That's why it makes more sense to look for it using space-based infrared telescopes. And that's the idea behind this new study. The team started digging through archives, searching for old infrared sky survey data, and they pulled it from two main sources. First, IRIS, a satellite launched in the 80s that scanned the sky for almost a year. Then, the Japanese satellite Akari, another infrared observatory that operated between 2006 and 2011. So basically, they compared objects that showed up in IRIS database and noticed which ones had moved by the time Akari took its observations. And by doing that, the researchers found something incredible, an object that might just be our long-lost ninth planet. Because if something moves, it could be a planet orbiting the Sun, right? And yeah, they did find some celestial objects showing tiny movements. But before jumping to conclusions, they had to rule out the parallax effect. And that's something really important when we're talking about solar system discoveries. To explain it, I need you to do something. Hold one finger in front of your face. Close one eye, and now switch. Your finger seems to move a tiny bit, right? That's because you're looking at it from a slightly different angle, from one eyeball to the other. The same thing happens when we look out into space from Earth. Since our planet orbits the Sun, our view of very distant objects shifts just a little. That effect is called parallax. My point is, because of this effect, Planet 9 would appear to move across the sky as Earth goes around the Sun. On any given day, it might seem to be in one spot, but 6 months later, when Earth is on the opposite side of the Sun, it would look like it shifted. 6 months after that, it would seem to move back again. Scientists had to account for parallax. Actually, they had to remove its effects. So the team looked at images of the sky taken on the same date every year. Because on that same date, Earth is always in the same spot in its orbit. That means if Planet 9 is real, it would show up in the same place in those images every year. No fake wiggle from parallax, just its real position. This careful search led them to a single object, a tiny dot in the infrared data. This strange little spot had moved slightly along its orbit around the Sun over the 23 years between Iris and Akari. Wait, could that be it? Did astronomers just confirm a hidden planet? Well, maybe. But don't get too excited. The data we have on its motion over that time is not enough to figure out its full orbit. So, for now, we still can't say for sure if this mysterious object is really Planet 9. It's definitely a strong candidate, though. Based on how bright the object appears, the team estimates it could be pretty massive, and that came as a big surprise. You see, previous NASA research ruled out any Jupiter-sized or Saturn-sized planets hiding out there, but a smaller world would have gone undetected. So the scientists were looking for something just a bit bigger than Earth. But it turns out this mysterious planet might be more massive than Neptune. Now that they've discovered Planet 9, supposedly at least, the plan is to keep tracking it and collecting new data. But don't think the road ahead will be easy. Because since the Akari satellite spotted it for the first time, that object didn't just sit still. It's been moving slowly through space ever since. So now scientists need to use regular telescopes on Earth to look for it again. And here's the tricky part. They're not exactly sure where it moved to, so they have to search a pretty big patch of the sky. And so far, no matching object has been found. Whether this really turns out to be the Planet 9 discovery or not, only time will tell. For now, its existence is still up for debate. But with powerful new technology on the way, like NASA's Nancy Grace Roman Space Telescope, astronomers are more determined than ever to uncover the truth. And if Planet 9 really is out there, hiding in the cold, dark edges of our solar system, it's running out of places to hide. Now picture a strange world where molten metal falls from the sky. A planet where it rains glass, sideways. A place where the winds are many times the speed of sound. Even though these planets sound like stuff from a nightmare, they do exist. Would you survive on any of them? Nope. But come on, let's see why. Now, brace yourself, and I mean it literally, because WASP 127b is terrifyingly windy. On Earth, our most powerful storms produce winds around 200 miles per hour. And even Neptune, the windiest planet in our solar system, tops out at about 1,100 miles per hour. But on 127b, winds dash across the equator at a staggering 20,500 miles per hour. That's 35 times faster than a jet and faster than the speed needed to orbit the Earth. 127b orbits a star similar to our Sun, but it's super close to its parent star, only 4.3 million miles away. That's why it takes just 4.2 days to make a full orbit. The heat there is insane. Cloud tops reach 1,800 degrees Fahrenheit, which is enough to melt almost, anything. And 127b is supermassive. Well, kind of. It's a gas giant with a diameter 1.3 times that of Jupiter, but only 1/6 of Jupiter's mass, which makes it a giant, hot, puffy balloon floating in space. The planet's atmosphere is so expanded that it's basically a boiling, raging storm globe, completely unlivable. If you somehow ended up on 127b, survival would be, well, impossible. The winds would toss you around, the extreme heat would cook you, and the planet itself would offer no solid ground to stand on. You wouldn't be able to breathe, move, or survive even for a second in these extreme conditions. But shockingly, that's not the worst planet you could land on. Imagine a world where it literally rains iron. This is WASP-76b, a planet so close to its star that the day side scorches at over 4,300 degrees Fahrenheit, hot enough to vaporize metals into gas. The night side is cooler, but still a blistering 2,500 degrees. Such a temperature makes those metals condense into clouds and rain down, like molten malted milk balls falling from the sky. The planet orbits its star every 43 hours, and it's tidally locked, which means that one of its sides always faces the star. The winds on the planet are absolutely insane, blowing up to 11,200 miles per hour. They zoom across the planet, fueled by the extreme temperature difference between day and night. And 76b is huge. It's a gas giant twice the size of Jupiter. It's practically sitting on the edge of its star's outer atmosphere. Scientists say we don't fully understand the physics here. Eventually, this planet could spiral into its star, or radiation could strip away its atmosphere, leaving only a scorching rocky core. Now, a human on 76b wouldn't last a fraction of a second. The day side would instantly vaporize you, just like the night side. And don't forget about the winds. You'd be ripped apart before you even touch the ground. And iron rain would slam down around you like fiery pellets. Sounds like a place to avoid. Now, if you're looking for long-term real estate investments, avoid WASP-12b. This planet is over 1,300 light-years away in the Auriga constellation. It orbits its sun-like star extremely closely, completing one orbit in just over one Earth day, about 26 hours. The planet's surface temperature reaches nearly 4,600 degrees Fahrenheit. It is 40% more massive than Jupiter, but powerful tidal forces stretch it into a football shape. But the main problem is that the atmosphere of this planet has expanded to nearly 3 times Jupiter's radius and is being pulled onto the star. And that means the planet is slowly being destroyed. Astronomers think that in about 3 to 10 million years, the planet could be gone for good. They found a huge cloud of stuff flying off the planet, including chemicals never seen on other planets before. No one would survive on 12b. The surface temperature is hotter than molten lava or any furnace on Earth. Any protective suit would fail instantly. The atmosphere is being ripped away by the planet's star, so there's no breathable air, just superheated hydrogen and helium streaming away into space. Plus, the gravity is extreme, so moving there would be, well, impossible. In any case, you would be vaporized almost instantly before trying to take a step. But however bad this planet sounds, the next world on our list beats it, because it rains glass on this planet. HD 189733b, I'll just nickname it Bubba, is a truly terrifying place, just 64.5 light-years from Earth. It's a gas giant, slightly bigger than Jupiter, and about 11% wider. But don't let that fool you. This world is a nightmare. Winds roar across the planet at up to 5,400 miles per hour, which is about 7 times the speed of sound. Temperatures soar between 1,600 and 2,200 degrees Fahrenheit, hot enough to melt metal. The planet also spins incredibly fast, completing one orbit in just 2.2 days. It races around its star at roughly 341,000 miles per hour. Its cobalt blue color comes not from water, but from a scorching, hazy atmosphere filled with silicate clouds. These clouds can condense into glass, and the planet's hurricane-force winds likely fling it sideways, making the rain fatal. Bubba is a hot Jupiter, a huge gaseous planet racing in a tight orbit around its star. It's also one of the most extreme, hostile worlds astronomers have ever found. If you somehow ended up in this world, survival would be out of the question. The heat alone is lethal. Insane winds would slam you around. An umbrella wouldn't save you from glass raining sideways, which would shred you in seconds. In short, you wouldn't last a heartbeat in this inhospitable world. But there's a planet that makes almost every other world look tame. It's Gliese 436b. It's small for an exoplanet, roughly the size and mass of Neptune, but don't let that fool you. Its proximity to its star turns it into one of the most extreme planets we know. 436b orbits a red dwarf star just 2.5 million miles away. To put that into perspective, Mercury, the closest planet to our Sun, is nearly 36 million miles out. This means that 436b races around its star every 2 days and 15.5 hours. That's lightning fast. A year there is shorter than a long weekend on Earth. The surface temperature is a balming 820 degrees Fahrenheit, which doesn't sound too bad in comparison. But there's the twist. The planet is covered with ice. Now, that's not ordinary ice, though. This is Ice 7, a dense, crystalline form of water created under unimaginable pressure. Imagine water so tightly packed that instead of melting under extreme heat, it remains solid. Scientists call it burning ice, and it's a form of ice that Earth laboratories can only replicate under controlled conditions. The atmosphere of the planet is just as bizarre. The planet is mostly hydrogen, like a gas giant, but it contains 7,000 times less methane than expected. Instead, astronomers find a surprising amount of carbon monoxide, which shouldn't survive in such heat. To make it even stranger, 436b is losing its atmosphere. The planet is wrapped in a huge cloud of hydrogen, probably pushed out by the strong gravity from being so close to its star. This cloud is 50 times bigger than the star itself. Unlike a comet's tail, it doesn't get blown away. It follows the planet. Astronomers think that 436b has already lost up to 10% of its atmosphere. Now, if a human, like you, somehow landed on Gliese 436b, survival would be impossible from the first second. The surface temperature is hot enough to vaporize skin and incinerate anything exposed. The gravity is crushing because the planet is dense and packed tightly with matter, which would make a person feel like trying to lift a car with every step. Even worse, can it get worse? Yes. The atmosphere is mostly hydrogen with high levels of carbon monoxide. Breathing would be instantly toxic, and a single inhale would shut down your lungs. And that burning ice is so solid under pressure that even if you somehow avoided the heat and toxic air, the ground itself would be a strange, brittle, crystalline surface that could fracture or collapse underfoot. Add to that the planet's rapid orbit. Completing a full year so fast means winds and atmospheric currents are extreme. No shelter, no suit, and no parachute could protect you. In short, you would be instantly boiled, crushed, and poisoned, all while the strange, dense ice underfoot refuses to melt. Well, bye-bye. Now it seems there's new solid evidence that Mars once had rainforests, real rainfall, and long-lasting rivers. NASA's Perseverance rover found a mineral called kaolinite on the floor of Jezero crater. Down on Earth, this stuff only forms in warm, wet places with heavy rain that lasts for millions of years. And this kind of rain feeds jungles, not deserts. That means Mars had showers for a long time. And that changes everything we thought we knew about the planet. So that mysterious kaolinite doesn't form from a quick flood or a melting glacier. It forms when liquid water keeps soaking into rock over insanely long periods, breaking it down grain by grain. When Perseverance spotted kaolinite pebbles and boulders scattered across Mars, scientists realized Mars once behaved less like Antarctica and more like the Amazon. That tells us that ancient Mars had a stable climate, thick enough for atmosphere, and a functioning water cycle with clouds, rain, and runoff. The place where the kaolinite showed up, Jezero crater, is pretty cool itself. It used to be a massive lake, fed by rivers that carved channels you can still see today from orbit. Scientists think those rivers could have washed the kaolinite into the crater like a conveyor belt of rainforest soil. Another theory is that a meteor impact blasted the material out of nearby terrain and dropped it there like cosmic shrapnel. Either way, water clearly moved these rocks around, and moving water is a huge deal because stagnant water doesn't shape landscapes like that. Every form of life we know depends on liquid water. Not ice, not vapor, liquid water that sticks around. A warm, wet Mars with rainfall would have had streams, wetlands, and chemical reactions happening non-stop, which are the same ingredients Earth used to kickstart life. Now, this doesn't mean Mars definitely had some creatures waving at the sky, but the planet checked way more boxes for habitability than we ever expected it to. For decades, Mars looked like a planet that maybe thawed for 5 minutes and then froze forever. Now it looks more like a world that stayed comfortable for hundreds of millions of years before everything went wrong. Scientists think Mars lost its atmosphere because it lacked a strong magnetic field, which is like a shield that protects planets from the solar wind, a constant blast of charged particles from the sun that can strip a planet bare over time. While all that rainforest talk grabs headlines, Mars keeps stacking surprises. In 2025, scientists spotted skylights on Mars. Those are giant holes in the surface of the red planet that drop straight down into underground cave systems, which formed long ago. On Earth, caves like this protect life from radiation, temperature swings, and surface chaos, which makes them perfect hiding spots if ancient Martian life ever existed. Some of these caves might be karstic, which means slightly acidic water slowly dissolved the rock, carving out underground chambers over time. That process needs liquid water and patience, which Mars apparently had plenty of back in the day. Scientists suspect these caves could trap ice, preserve chemical fingerprints of life, or even lock away organic material untouched for billions of years, like a time capsule no one has opened yet. The caves sit in a region called Hebrus Vallis, tucked between an old volcano and a massive plain in Mars's northern half. This area doesn't show signs of lava tubes, which scientists already know exist on Mars. Instead, it shows ancient river channels, hydrated minerals, and sediments that only form when water sticks around. Scientists spotted 8 skylights and knew they weren't impact craters because nothing splashed outward when they formed. The surface simply collapsed into empty space below. Researchers pulled this story together using old Mars mission data, including mineral maps, hydrogen readings that hinted at buried water, and ultra-sharp images from orbit. The big deal is this: caves protect things. They block radiation, trap ice, and preserve chemical traces far better than the surface ever could. If Mars ever hosted life, even tiny microbes, those caves rank among the best places to find what's left. Now, a year earlier, in July 2024, the Perseverance rover drove along what used to be a river billions of years old. After the river dried up, part of a rock face broke loose and fell into the channel. Perseverance found it sitting there, untouched for ages. Scientists named it Sheyava Falls. The rock's surface showed tiny dark spots scientists nicknamed poppy seeds, and larger pale blobs with dark rims called leopard spots. When Perseverance zoomed in, it also detected organic molecules. These are carbon-based compounds, the same basic ingredient every living thing on Earth uses. Scientists predicted years ago that if Mars ever hosted microbes, rocks like this one would exist. These spots matter because life needs energy. Some organisms use sunlight, others eat chemistry. Microbes can survive by moving electrons between chemicals, kind of like stealing spare batteries to power themselves. At Sheyava Falls, scientists think microbes could have taken electrons from organic compounds and handed them to iron in the rock. That reaction releases energy that microbes can use to survive. So, Sherlock, the evidence lines up. The dark dots and rims contain a mineral called vivinite, which only forms when iron gains electrons. When iron changes this way, it loses its rusty red color and turns pale. That explains why the centers of the leopard spots look lighter. Perseverance also found another mineral there called greigite. Greigite needs sulfide to form, and microbes can create sulfide by feeding electrons to sulfate, another chemical found in the rock. Now, scientists can't fully analyze this rock yet, but they already have one tool down on Earth, the kind so small you'd miss them unless you knew exactly how to look. If microbes ever lived in Mars's ancient oceans, they probably didn't leave skeletons or bones. They left chemical fingerprints locked inside minerals. On Earth, microbes showed up in oceans about 3.7 billion years ago, give or take. Mars had water around the same time. When water evaporates, it leaves minerals behind, and some of those minerals can trap microorganisms like bugs and amber. On Mars, scientists expect sulfate minerals to play that role. On Earth, gypsum does the same thing. To test this idea, researchers went to a gypsum quarry in Algeria. Millions of years ago, the Mediterranean Sea almost dried up and left thick gypsum layers behind. Those layers preserved ancient bacteria inside them. All this makes the site a perfect Mars stand-in. The team tested a compact device called LIMS, which is an easier way of saying laser ablation ionization mass spectrometer, which I'm only going to say once. A laser zaps a tiny spot on a rock, vaporizes it, and then reads the chemical elements released. Each element leaves a unique signal, like a barcode. That lets scientists spot chemical traces linked to life. When they aimed LIMS at the Algerian gypsum, scientists found thin, thread-like structures already known to be bacteria. They also spotted minerals that microbes help create, like dolomite and certain clays. That matters because microbes don't just leave fossils, they change rocks while they live. Mars makes this harder, though. Its environment differs from Earth's, and any fossils there would be billions of years old, not millions. Scientists also need to rule out non-living processes that could copy these signals. Now, lots of people think that to find all the answers, humans must go to Mars. And the number one goal for the first human mission to Mars is finding life, not digging up resources or setting flags. Scientists want to know if Mars ever hosted living organisms, if it still does today, or if the planet once ran the chemical experiments that led to life. After that, researchers want to understand where Mars keeps its water and carbon dioxide, how those cycles work, and how they changed over time. Geology comes next because rocks keep the planet's memory. Every layer tells part of Mars' story. Scientists need to understand how Mars affects the human body, the brain, and even group dynamics when people live together in isolation. Long-term plans go even farther. Scientists want to learn how plants, microbes, and animals survive on Mars, how radiation alters DNA, and whether reproduction works across generations. They also want to know if Martian microbes could harm astronauts or equipment. So, planets with two suns, like Tatooine from Star Wars, used to sound like pure fantasy. For decades, scientists believed these systems were too unstable to exist. Two stars tugging at a planet should fling it into space or drop it into one of the suns. Except, it turns out that nature didn't get the memo. Astronomers have found a planet calmly orbiting two stars like it's no big deal. This planet lives closer to its two parent stars than any other directly imaged planet in a binary star system astronomers have ever seen. Now, direct imaging means they saw the planet's light, not just its shadow. The whole system sits about 446 light-years away, so the light we see from it today left before humans ever built modern cities. This space monster is roughly 6 times the mass of Jupiter. And even more surprising, the planet is only about 13 million years old. That sounds ancient until you zoom out a little. Earth is about 4.6 billion years old, which makes this planet basically a newborn in cosmic terms. The two suns of this monster orbit each other incredibly fast and complete a full loop in just 18 Earth days. That means their gravity constantly shifts, yanking space around them like a cosmic washing machine. Even so, the planet stays locked in its path, so it takes it 300 Earth years to finish a single orbit. So nobody fully understands how this planet formed in the first place. When two stars orbit each other this closely, their gravity usually tears apart planet-forming material before anything big can take shape. Scientists have only found a few dozen planets like this so far, and that's nowhere near enough to piece together the full story. To solve the mystery, they need more data. Now, another cool find that still needs more research is a planet so stretched by gravity that it looks like a lemon, not a sphere. This planet is nothing like the calm blue and green worlds we see in space movies. It orbits a pulsar, which is basically a star's corpse. When a massive star expires, it collapses into an ultra-dense object that spins insanely fast and blasts radiation like a cosmic lighthouse. Being near one of those means game over for anything solid. And yet, this planet hangs on, barely. The gravity stretches it, pulling harder on the side facing the pulsar than the far side, like cosmic taffy. And here's where it gets extra unsettling. When scientists analyzed this planet's atmosphere, they didn't find water or oxygen. They found helium and pure carbon. No clouds, no oceans, no chance of life. According to everything we know about planet formation, this world shouldn't exist at all. So it might not be a planet in the normal sense. It could be the exposed core of a star that got shredded, leaving behind something stuck between planet and stellar corpse. That's a pretty scary trend. The line between planets and stars keeps getting blurry. And speaking of scary, meet this guy. This system lives around two red dwarf stars. These two stars orbit each other at a distance similar to how far Jupiter sits from the Sun. Scientists found two Earth-sized planets and a third possible one squeezed right up next to the stars. One planet completes a full year in just over 2 days. Another takes about 3.5 days. The candidate planet orbits even faster. To put that in perspective, these planets sit less than 2 million miles from their star. The Moon sits about 250,000 miles from Earth. So yeah, these worlds are close. When they combined data from space and ground-based telescopes, astronomers realized they were staring at something totally new: planets that transit or pass in front of both stars. Most planets in double-star systems orbit only one star, and this setup shouldn't last long according to the rules of physics. But these planets exist anyway, calmly breaking the rules. So this guy proves that planet formation works in ways we still don't fully understand, and space clearly enjoys messing with our expectations. Now, let's crank up the horror a notch. Astronomers made the first ever 3D map of a planet outside our solar system. And not just any planet. This one is so hot it literally tears water molecules apart. As the planet moved behind its star, the James Webb watched tiny changes in the star's light at different colors or wavelengths. Some colors get absorbed by water vapor, others don't. By stacking all that info together, scientists figured out temperatures at different heights and locations in the planet's atmosphere. And that's how they learned that parts of its atmosphere heat up to nearly 5,000 degrees Fahrenheit, hotter than molten lava. This superhot planet sits about 400 light-years away and weighs around 10 times as much as Jupiter. It races around its star in just 23 hours. 1 year there is basically a day. And because it's so close, the temperatures get so high. Winds try to move heat around, but they totally fail. WASP-18b's atmosphere barely has any water and instead overflows with carbon monoxide. Astronomers once believed water should be common in giant planet atmospheres. This world proves water is optional, not guaranteed. Now, magma worlds are another perfect proof of that. There's a huge group of planets called sub-Neptunes, planets bigger than Earth but smaller than Neptune. For a while, some scientists hoped these worlds were Haitian planets, covered in deep oceans of water or ice, wrapped in thick atmospheres. One famous example was K2-18. Its atmosphere showed methane and carbon dioxide, but almost no ammonia. But as it turned out, lava dissolves ammonia too, so the missing ammonia doesn't prove water at all. It could just mean the planet has a global ocean of magma instead. The researchers model how these planets heat up, cool down, and evolve over time. They asked a simple question: do these planets ever cool enough to stop being lava worlds? And the answer was almost never. When they tested thousands of known sub-Neptunes, they say almost all of them are likely lava worlds, not water worlds. In simple terms, these planets don't breathe water vapor, they breathe rock vapor. Their atmospheres come from magma boiling, not oceans evaporating. And that changes everything. Many worlds we once labeled maybe habitable turn into hellscapes the moment you run the numbers honestly. And that means space isn't hiding Earth clones, but mass-producing furnaces and other sorts of monsters. Take this bad boy, for instance. It sits only about 64 light-years away, which is uncomfortably close in cosmic terms, and it's the nearest hot Jupiter to Earth. From afar, it looks stunning, a smooth, deep blue marble floating peacefully in space. But that color hides something absolutely brutal. On this planet, it rains glass, sideways. Winds scream across the atmosphere at around 5,400 miles per hour, fast enough to shred anything instantly. The blue color comes from tiny particles of silicate, the stuff glass is made of, floating in the air. The planet's surface temperature hits about 2,400 degrees Fahrenheit, hot enough to melt rock. That heat turns those silicates into microscopic shards of glass that whip around the planet like a worldwide sandblaster. Standing there wouldn't hurt. You wouldn't exist long enough to ever feel it. And then there's the darkest planet ever found. It reflects less than 1% of the light that hits it. It's darker than coal, darker than black paint. Light just disappears into it. Not all planets even bother with stars at all. Astronomers have found rogue planets, worlds kicked out of their solar systems. These lonely planets drift through space in total darkness, frozen and untethered, with no sunrise ever again. Now, all of this shows us that our universe isn't designed for life. Life survives despite the universe, not because of it. Earth isn't typical, it's lucky. We're only at the beginning of this discovery era. Every year, new telescopes sharpen the picture, and every year, the picture gets stranger. The more clearly we see the universe, the less it resembles our imagination. And that's the most unsettling truth of all. For what seems like ages, scientists have been hunting for another Earth, perhaps to find cosmic neighbors, or maybe just to have a backup planet for potential relocation in case we can't turn this one around. Now, thanks to the James Webb Space Telescope, they might finally have a strong candidate. It's called TRAPPIST-1e and is located 40 light-years away. 1e orbits a small star called TRAPPIST-1. It's an intriguing system that has 7 Earth-sized planets, all of which are nicknamed with letters from B to H. While 40 light-years won't be reachable anytime soon, that's still close. Well, in space terms at least. Our galaxy, the Milky Way, is about 100,000 light-years across. So compared to that, 40 is like a walk down the driveway. Or at least will be if our spaceships achieve a speed close to the speed of light, just like in the movies. Remember, a light-year isn't a measure for time. It's how far light can travel in 1 year, which is close to 6 trillion miles, which is a lot of zeros. So, multiply that by 40, and you get the location of TRAPPIST-1. So, bring a big lunch. T1 is a red dwarf, a type of star that's basically like a dimmer and smaller version of our Sun. It's only a bit bigger than Jupiter. Among this family, 1e sits in the star's sweet spot, the so-called Goldilocks zone. Not too hot, not too cold, at a distance where liquid water could exist on a planet's surface if it has the right atmosphere. Perfectly habitable, at least for creatures resembling Earth's residents. However, it's not just located at just the right distance, which is a huge plus. 1e also happens to be a rocky planet. Its size and mass are close to Earth's, which suggests it has a similar density and structure, as well as similar gravity, meaning no cool jumps like on the Moon. Now, Webb has picked up hints that there could be an atmosphere. The planet might be wrapped in gases like nitrogen, carbon dioxide, and methane. We have such a mix over here, too. Earth's air is built from the same elements. Atmosphere matters. Mars lost most of it, Venus has too much, and Earth got it just right. That's why we have cozy weather and oceans. If 1e really does have something similar, it could mean clouds, rain, and maybe even seas. The stuff that would make Earthlings feel at home. However, here is where it gets interesting. We mentioned that 1e is a red dwarf star, and that makes it dim, hundreds of times dimmer than the Sun. If you were standing on 1e, the star would look way bigger in the sky than our Sun does here. But it would glow red and dull. It would be like living under a never-ending sunset. You might think, sweet, it would be romantic, until it gets old. I mean cold. It has to be freezing, right? After all, how can such a faint star provide enough heat for life the way our sun does? Well, funny enough, you won't need super winter-resistant jackets. The trick is distance. TRAPPIST-1e orbits extremely close to its star, just about 3% of Earth's distance from the Sun. If the planet were sitting where Earth is, it would be a ball of ice. But being so close also means that its year is only around 146 hours. That means it takes 6 Earth days for 1e to resolve around T1. Celebrating birthdays every 6 days sounds like a great deal, huh? That's a lot of cake. But wait, does that mean that each season would last about 36 hours? No, because the planet is almost certainly tidally locked. That means one side bakes in endless daylight and the other side is stuck in eternal night. Not exactly Earth 2.0. Without an atmosphere, you'd get a scorched wasteland on one side and an ice cube on the other. But with an atmosphere, the air can spread the heat around, smoothing things out. In theory, the comfiest spot might actually be the twilight strip between day and night, the so-called Terminator line. Again, a permanent sunrise or sunset. Instagrammers would love it. Red dwarfs are actually the most common stars in our galaxy, making up about 70% of all the stars we know about. And they live practically forever. Our sun is projected to last 10 billion years. Red dwarfs could go on for trillions. It's more than enough time for life to develop. However, the short straw is that red dwarfs are kind of feisty. They erupt with powerful flares that blast out intense radiation. So, for planets orbiting so close, those flares can strip away atmospheres and sterilize the surface. It's like having a dream house with a beautiful view near a dynamite factory. Oops. That's what makes TRAPPIST-1e so exciting. If it does have an atmosphere, it would mean it somehow resisted billions of years of flare activity. And it might not be the only one. There could be plenty of exoplanets like this out there. Now, you may be wondering how scientists could possibly know what's going on with a small planet that's so far away. Well, they study light using a technique called transit spectroscopy. When TRAPPIST-1e passes in front of its star, the light filters through its edges, revealing clues about its air. Repeat enough times, and we start to see what it's really like. That's one of the most important features of the James Webb Telescope. It doesn't just snap pretty pictures. It dissects that light into thousands of slices, each revealing a different clue. It's also great when you remember that E1 is just one of 7 planets that orbit so close. So scientists have a lot to study in that part of the universe. Each transit gives them a little more data, and after enough passes, they can start to rule things out. No thick hydrogen blanket? Check. No Venus-style carbon dioxide swamp? Looking that way. What's left is a planet that might, just might, have something closer to Earth's atmosphere. In other words, nobody's sending probes to TRAPPIST-1e anytime soon. But with telescopes like Webb, we can already peek at its air from across the galaxy. If you follow space-related news, you are already aware that 1e isn't the first so-called Earth-like planet that reached headlines. Astronomers have been teasing us with candidates for years, and each one comes with a but. As in, however, not your butt. For example, Kepler 186f. Back in 2014, it was the first Earth-sized planet spotted in the habitable zone of its star. People were really excited. NASA even made a sci-fi-style travel poster. The catch? Oh well, just one minor thing. The fact that it's about 500 light-years away. Even if we build a spaceship that could cruise at 1/10 of light speed, which we can't, it would still be a 5,000-year-long trip. Then there's Proxima Centauri b. This one is close, just 4.2 light-years away, orbiting the nearest star to our Sun. On paper, it's a dream. However, its star is even moodier than T1. Proxima exhales massive radiation flares regularly, which makes everything unpredictable and unstable. And then we have K2-18b. The James Webb Telescope actually spotted methane and carbon dioxide in its atmosphere, gases which might hint at biological activity. Sounds great, except the planet is more like a mini Neptune. probably wrapped in thick gas layers and unlikely to have a solid surface to stand on. The bottom line? When compared to all these, TRAPPIST-1e looks like the most promising one. Close enough to study, rocky enough to stand on, and sitting in a sweet spot where liquid water could exist if conditions line up. Of course, we still need more data. 1e could turn out to be a barren rock. But the bigger story is that we're getting better at this. A few decades ago, we didn't know if other solar systems even existed. Now, we've found over 6,000 exoplanets, with more getting added almost every week. Odds are, plenty of them will be rocky, Earth-sized, and orbiting in the Goldilocks zone. Maybe we can't go there, but they could mean the discovery of extraterrestrial life. That's the exciting part. Every time Webb or the next generation of telescopes take a look, we inch closer to answering the big question: are we alone, or is the universe full of neighbors? Hey, get your dog off my lawn. Hey, scientists may have just found a new planet that looks a lot like Earth, with a big icy catch. This world is about 150 light-years away, rocky, and circles a sun-like star on a schedule pretty close to ours. At first sight, it sounds promising, right? Well, slow down. There's a catch here. It might be insanely cold as Mars in the deep freeze. You see, HD 137010b, that's a mouthful, doesn't seem to be a gas ball, so we would probably be able to stand on its surface. It's a little bigger than Earth and goes around a star that's pretty similar to our Sun. This star is about 146 light-years away from our planet, which, in space terms, is close enough for scientists to study it instead of just, squinting at it. But what made people excited is the fact that this planet takes about 1 Earth year to go around its star. Now that's a big deal, because most exoplanets dash around their stars in days or weeks. Even better, this newly discovered one might sit right on the outer edge of the habitable zone, also called the Goldilocks zone. This region is not too hot and not too cold, which means that liquid water might exist on the planet if it has the right atmosphere. A big if, but still cool. Another thing that makes this planet extra special is how we see it. From Earth, it actually passes in front of its star. Imagine a tiny bug crawling across a flashlight beam. You got it. That makes it way easier for scientists to study things like its size, orbit, and maybe even what its atmosphere is made of. And if all of this checks out, it could be one of the best Earth-like planet candidates we've ever found. And now, the bad news. This planet does not get much sunlight. HD 137010b gets less than 1/3 of the heat and light Earth gets from the Sun. Even though its star is similar to our Sun, it's basically the Sun's quieter, dimmer cousin. Same type, lower wattage. What does that mean for the planet? It could be insanely cold. Scientists think the surface temperature might max out at around minus 90 degrees Fahrenheit. And that's not a grab-a-jacket cold, that's your face freezes right away cold. For comparison, Mars has an average temperature of around minus 85 degrees Fahrenheit. So this planet could actually be colder than Mars, a frozen desert, not to be confused with a frozen dessert, that looks like it gave up on life a long time ago. Another plot twist: this planet isn't officially a planet yet. At the moment, it's still labeled a candidate. Scientists usually confirm planets by watching them pass in front of their star over and over again. Every time that happens, the star dims just a little bit. But with this new space body, we've only seen one transit, a single 10-hour-long mini-eclipse, spotted during Kepler's second mission, called K2. Even with that one pass, astronomers could still learn a lot. They measured how long the planet's shadow took to cross the star, about 10 hours. For comparison, Earth takes about 13 hours to cross the Sun. Then, they plugged that into orbital models and estimated that the planet probably takes about a year to go around its star. That's impressive, but it's still not enough. Astronomers need to see that dip in starlight repeat on schedule to be sure it's really a planet and not some weird stellar wanderer. Unfortunately, this planet orbits far out, and those transits are rare. You don't get one every few days or weeks. You might have to wait a year or more for the next one. That's one of the big reasons Earth-like planets are so hard to find in the first place. So now, scientists are just hoping that other space telescopes can help out. NASA's TESS might catch another transit, or Europe's Cheops telescope could help pin it down. If neither of those catches it, we might have to wait for the next generation of space telescopes to get better data. Because even though this planet sounds like an ice cube in space, it's not totally doomed. If it has a thick atmosphere, especially if it's rich in carbon dioxide, it could trap heat really well, like a planet-sized winter coat. In that case, the planet might actually have a mild climate, or even liquid water on its surface. Well, based on computer models, scientists say there's about a 40% chance this distant world sits in the safe, conservative, habitable zone. A chance that is located in a more relaxed, optimistic habitable zone reaches 51%. But there's also a 50-50 chance that the planet is actually outside the habitable zone altogether. In other words, this planet is basically a cosmic coin toss. It could be a frozen wasteland, worse than Mars, a chilly, barely survivable world, or a watery planet hiding under a thick atmosphere. HD 137010b isn't the only place that has the potential to host human civilization in the future. In recent years, astronomers have been spotting new super-Earth planets orbiting remote stars. Now, checking our space vocabulary, super-Earth means a planet beyond the solar system with a mass higher than that of Earth, but below those of the ice giants of the solar system, Uranus and Neptune. One of those planets is Gliese 667cc. It's just 22 light-years from Earth. But even though it seems pretty close, it's still around 129 trillion miles away from us. That's around 1.4 million times the average distance from the Earth to the Sun. So very, very far. The planet itself is around 3.8 times as massive as Earth and completes one orbit around its host star within 28 days. In other words, a year on that Earth-like planet is 13 times shorter than a year on our planet. Luckily, the star is a cool red dwarf, so the exoplanet most likely lies in its habitable zone. But there's still a chance that this world might be regularly baked by the flares from its parent star. Then there's Kepler-22b. This world is way farther away than the previous world, more like 600 light-years away from our planet. It's larger than Earth and is about 2.5 times our planet's size. Sadly, we still don't know whether this planet is rocky, liquid, or gaseous. The orbit of Kepler-22b is pretty similar to Earth's. It takes the planet 290 days to orbit its G-class star, which is kinda similar to our Sun. But this star is smaller and colder than ours. Now, don't confuse this world with Kepler-69c. It lies a whopping 2,700 light-years away from us and is almost 70% larger than Earth. Researchers know nothing about its composition, but they found out that the planet needs 242 days to complete one orbit. This makes its position in its system similar to that of Venus in our solar system. At the same time, this world might be more hospitable than Venus since its host star is a bit less luminous, 80% of our Sun. As for our Venus, it's an extremely hostile place. You don't want to go there. A runaway greenhouse effect caused by an atmosphere that's about 96% carbon dioxide traps the heat. That pushes surface temperatures up to around 878 degrees Fahrenheit, which is hot enough to melt lead. On top of that, the air pressure is about 90 times stronger than that of Earth, and the whole planet is covered in thick clouds of corrosive sulfuric acid. Oh boy. Compared to our neighbor, TOI 733b seems like a pretty friendly world. This planet was found in 2023. It's floating 245 light-years away from Earth. The coolest thing about this planet is that it might have a massive ocean. According to scientists, this planet is likely to be completely covered with water. Does it mean there could be life on this super-Earth? Well, time will show. And who knows? Maybe soon we'll find even more planets that could become a new home for people looking to explore the universe. As for HD 137010b, the fact that it checks so many Earth-style boxes makes it a really interesting find. It's not a backup Earth yet, but it makes scientists stop and say, okay, this one's worth a closer look, or something similar.
Africa is ripping itself apart. A giant crack is tearing through the continent and stretching south like a zipper being pulled open. And it's happening faster than anyone expected. Now, scientists think the main trigger might not be buried deep inside Earth, but up in the sky. That's right. What might be speeding up this breakup process is the region's drying climate and brutal droughts. And that feels off, right? Usually tectonic plates move first and the climate changes afterward, but in East Africa, it might be flipped. The climate may actually be helping the plates pull apart faster. But first, let's look at what's really going on there. So, Earth's crust isn't one solid shell. It's made of giant tectonic plates, massive slabs of rock that never stop moving. They grind past each other, collide, slide under, climb over, or stretch apart. This motion is so slow, we don't notice it. But over long periods, those tiny shifts reshape continents, just like what's happening in Africa. For about 30 million years, the Arabian Plate has been moving away from the African Plate. That slow pull split the land. The seawater rushed in to fill the gap, forming the Red Sea and the Gulf of Aden. And that's not the only breakup happening there. In Eastern Africa, the Somali Plate is stretching away from the Nubian Plate. This is opening up the East African Rift Valley, cutting right through places like Ethiopia and Kenya. The region where these plates meet has a name. It's a triple junction. But in this case, they aren't crashing into each other. All three tectonic plates are diverging. When that happens, the crust gets pulled in different directions at once, like fabric being stretched from three corners. It weakens, thins out, and cracks open. They're pulling apart at different speeds too. The Arabian Plate is moving away from Africa at about an inch per year. The two African plates are separating more slowly, roughly between half an inch and 0.2 inches per year. And as they open that gap, hot material from deep inside Earth rises up and hardens, creating brand new seafloor along the split. I know, a few inches per year sounds ridiculously slow, but what makes this event so fascinating is that we're watching it happen in real time. We can actually see Africa slowly breaking apart, and it's terrifying. Back in 2005, a 35-mile long rift that opened up in the Ethiopian desert. The crack is 20 feet wide in some places, which is roughly the size of a shipping container. This is just one example of how active the region really is. From space, satellite images show valleys and rifts slowly widening over time. And down on the ground, people are posting videos of places where the Earth has already split open, leaving big cracks and gaps. Roads, houses, even schools are getting torn apart. The whole area keeps shaking from earthquakes, and the volcanoes are very active. What I mean is, even though this splitting process is super slow, we can actually see it happening. And it's unstoppable. Experts believe this crack in the East African Rift Valley will become a gateway. Waters of the Indian Ocean will eventually invade the valley and fill the growing gap. That will help pull the land apart even more, and eventually it'll create a brand new ocean. And we know that can happen because Earth has done it before. That's exactly how the Atlantic Ocean formed about 180 million years ago, when South America and Africa pulled away from each other. If the East African Rift keeps opening up, parts of Eastern Africa, Somalia, Kenya, Tanzania, Mozambique, and a big chunk of Ethiopia could one day break away from the rest of the continent. That means countries like Zambia and Uganda could actually end up with brand new stunning coastlines. But don't pack your swimsuit yet. Unfortunately, none of us will be swimming in the waters of this future sixth ocean anytime soon. Scientists estimate the full split would take about 5 to 10 million years. That's basically forever in human terms. But in Earth terms, it's surprisingly fast, almost like record speed. Now, scientists are trying to figure out why it's happening so fast. I mean, faster than it should. And here's a new intriguing possibility: a drying climate. One of the biggest clues starts right here at Lake Turkana. This lake in Kenya is about 19 miles wide and it's up to 400 feet deep in some places. But that's nothing compared to more than 5,000 years ago, when the lake level was up to 500 feet higher. Back then, the continent was going through something known as the African humid period. It was a time when Africa was wetter than it is today, and the Sahara wasn't a desert at all. It was green, wet, and full of lakes, rivers, and vegetation. But since then, the whole region has shifted into a much drier phase. So researchers took sediment samples from the bottom of Lake Turkana to figure out past water levels and how sediment washed into the lake over time. And while they were doing that, they noticed something else. Those sediment layers preserved lots of tiny faults and even the fingerprints of ancient earthquakes. Wait, wow! That means Lake Turkana might not be a simple lake. It could actually be one huge crack in the earth that eventually filled up with water. In other words, it could be a direct result of this whole rifting process. And now scientists think the same thing might be true for other deep, narrow lakes in the region, like Lake Malawi along the Tanzania-Mozambique border. So, scientists came up with a wild theory. What if these lakes are helping split Africa apart faster? Okay, maybe the theory isn't that wild. After all, water can indeed affect tectonic plates. For example, when glaciers melt and disappear, all that weight is removed, and the land underneath slowly pops back up, kind of like bread rising after you take something heavy off of it. That's called isostatic rebound, and big amounts of water can do the opposite. They press down on the crust, which can also affect things like faults and earthquakes. At Lake Turkana, something interesting shows up in the data. After the African humid period ended, the faults around the lake started moving faster, by about 0.007 inches per year. I know, that's a lot of zeros. But over thousands of years, that extra push can add up. And it could help explain why earthquakes might be more common in the region today than they were around 8,000 years ago. The study then ran computer simulations and found two likely reasons the shaking and fault movement sped up. First, there's less water pushing down on the ground. With that weight gone, the faults can slide more easily, like loosening a vise that was squeezing two pieces of wood together. Second, there's a volcano on an island on the south side of Lake Turkana. Deep underground, it has a pocket of hot, molten rock. When the lake level dropped after the African humid period, the pressure on the earth below eased up, like taking the lid off a pot. That lets the rock underneath melt a bit more. The extra melt flows into the volcano's magma chamber, swelling it up like a balloon. And that extra pressure can jolt nearby faults and trigger more movement. So yeah, drought and falling lake levels could be speeding up the splitting process. But it's not like the climate is creating the rift from scratch. It's more like the ground is already under tension, and the climate is giving it a little extra push. The real reason Africa is breaking apart might be related to something called superplume, an enormous column of scorching hot rock rising from deep inside the Earth. Think of it like a balloon underground that's slowly filling up. As it pushes upward, it puts pressure on the crust above it. Over time, that pressure weakens the crust and slowly cracks it apart. And even though none of us will be alive to see the final result of this process, it's still amazing to realize that we're watching a continent split, almost in real time.
Did you know that the moon is rusting? No, not rustic, rusting. Well, that sounds impossible because rust needs oxygen, and the moon, well, it doesn't have it. Or so we thought. Apparently, Earth is leaking its air, and it's marinating the moon. It might have been like that for billions of years. What does this mean? And why do scientists say it's great news for a future lunar base? Well, let's find out. A few years ago, the Indian Space Research Organization sent a probe called Chandrayaan-1 to orbit the moon. Its mission was to take some nice pictures, but it also was carrying a NASA-built instrument designed to chemically map the surface. The readings came back showing something scientists didn't expect on the moon: hematite. It's an iron oxide, or in plain words, rust. It's the same red, rusty material that eats through your garden fence or a forgotten bicycle chain. Finding rust on Earth is normal because our planet is wet and airy. You need a strict recipe to make it happen. You need iron, you need water, and you need oxygen. The Moon already has the first ingredient for rust because its surface is rich in iron from billions of years of asteroid impacts. But the other two ingredients are missing. There is no atmosphere to provide oxygen, and there is no liquid water gathering on the surface. But it goes beyond that. Space actually hates rust. The Sun constantly blasts the Moon with the solar wind, a stream of fast particles made mostly of hydrogen. Well, these particles tend to strip oxygen away from rocks instead of adding it. All of that makes it obvious why hematite doesn't belong anywhere near our satellite. But these results don't lie. The presence of hematite means that somehow, despite the vacuum and the Sun's particle stream, the Moon is getting a steady supply of oxygen. It's not coming from deep space or the lunar core. Also, the rust isn't spread evenly. The data showed that the hematite is more concentrated on the side of the Moon that faces Earth. The far side is mostly clean. Now, the only oxidizer close enough to do the job is Earth. We learned at school that Earth's atmosphere ends at the Kármán line, about 62 miles up. That's where space officially begins. But that's just the thick part. In reality, Earth is wrapped in a gigantic invisible cloud of hydrogen called the geocorona. It's enormous. It glows in ultraviolet light, and it stretches almost 400,000 miles into space. That's farther than the Moon's orbit. This means that despite being very far away, the Moon is still within the outer edges of Earth's atmosphere. If you were standing on the Moon, looking back at Earth with a telescope that can see ultraviolet hydrogen, Earth wouldn't look like a blue marble. It would look like it's wearing a huge, fuzzy, glowing halo. Now, when we picture Earth and the Moon, we imagine a huge, clean gap between them. Two worlds separated by nothing. But that nothing isn't actually empty. The two are already connected by gravity, tugging on each other nonstop. But there's another kind of connection most people never think about. Earth is surrounded by an invisible force called a magnetic field. It's created deep inside the planet and stretches far out into space. We don't see it, but it's the reason compasses work and the Sun doesn't strip our atmosphere away. This magnetic field doesn't just stop at Earth's surface. It doesn't sit there like a perfect bubble either. The solar wind pushes on it non-stop, stretching it out behind Earth into a long magnetic tail that reaches hundreds of thousands of miles into space, like a tail trailing behind a moving comet. That tail is how Earth's oxygen ends up on the Moon. The Sun slams into Earth's upper atmosphere, knocking oxygen and nitrogen atoms loose and turning them into charged particles. Normally, they drift off into space, but because they're charged, Earth's magnetic field grabs them and sends them backward, down the magnetic tail. Most of the time, the Moon is off to the side doing its own thing. But once a month, right around the full moon, it slides straight into Earth's magnetic ponytail. Inside that tail, Earth blocks the harsh solar wind and gives the Moon a few days of calm. But it's still moving straight through particles leaking from Earth. Those particles collide with the surface and react with the iron in the soil. Repeat that long enough, and it adds up. Earth loses tiny traces of its air, and the Moon quietly collects them, using its weak gravity like a slow, patient net. It's like driving behind a dirty truck. Dirt flies off of it, but you don't really notice until it starts sticking to your windshield. The same thing happens on the Moon, except, no windshield. We actually have proof of this happening in real time. A Japanese probe called Kaguya was hanging out in lunar orbit, and its sensors spiked when the Moon passed through Earth's magnetic tail. It detected a surge of high-energy oxygen ions. Scientists call it the Earth wind. It acts like the solar wind, except instead of being hot particles from a star, it's made from leftovers of our own atmosphere. And this suddenly makes the Moon part of a much bigger story. Scientists think this kind of atmospheric escape can help explain what happened to planets like Mars. The red planet doesn't have a global magnetic field today, but long ago it probably did. When that shield failed, its atmosphere had a much easier time leaking away. Studying Earth and the Moon is like watching a version of that process on replay, just in slow motion. And it's not unique. Near the edge of the solar system, Pluto's thin atmosphere is slowly being stolen by its moon Charon. Ooh, larceny in space. Pluto's gravity is so weak that its atmosphere stretches far into space. When those gas particles drift close enough, Charon's gravity simply grabs them. No magnetic field needed, just a leaky planet and a nearby moon pulling the material away. Now, when the Apollo astronauts brought lunar soil to Earth, it was already loaded with hydrogen from the solar wind. The sun sprays the lunar surface with hydrogen, and over time, that hydrogen gets baked straight into the dust. That's the H, but you still need the O2 to create water. The regolith may already contain trace amounts of oxygen locked into minerals and dust, not as ice, but as something that can potentially be processed. It would mean that regolith is not just a nuisance that destroys gear and rovers. For a future lunar base, even small amounts matter. Water is heavy. Launching it from Earth is a nightmare. If the moon can supply even part of what astronauts need, it could make a difference. Now, another cool side effect of this discovery is that drilling into the moon could tell us more about Earth's history. You see, our planet is terrible at keeping records. It's like a giant recycling machine. It's always changing. Tectonic plates grind the crust down and melt it into magma. Winds and rains erode rocks. The air that we breathe now is different from the one that was around 2 billion years ago. Now, we can guess what the ancient atmosphere was like, but we don't have a physical sample. The moon is the complete opposite. It's cold and static. When those Earth particles land on the moon, they get buried under dust and stay there. They're trapped in the crystal lattice of the soil. Think of the lunar surface like an ice core in Antarctica. The deeper we dig, the further back in time we go. If we drill a core sample on the moon, we might, theoretically, find layers of oxygen and nitrogen from 2.5 billion years ago. That is right around the Great Oxidation Event, when microbes first started pumping oxygen into our atmosphere. That could tell us something we don't know. It could prove that life started earlier than we thought. It could show us exactly how a dead planet turns into a living one. That's another answer you can give the next time somebody asks why we should go back to the moon. Also define the green cheese. Hey, just Google it.
The Amazon rainforest is shifting into a climate that Earth hasn't seen in millions of years. Scientists looked at decades of real data and had to invent a new word for it: hypertropical. In normal human language, it means hotter droughts that last longer, hit more often, and push the rainforest past its limits. So yes, hypertropical is not a lush jungle, but extra, as you might think. It's more like a tropical forest, but stressed out, overheated, and drying out like a sponge left on a radiator. The researchers behind this say these conditions have no current analog. All this is pretty worrying since the Amazon acts like a giant carbon sink that absorbs carbon dioxide from the atmosphere and stores it in trees and soil. It's like Earth's lungs mixed with a massive storage vault. But when trees get hammered by heat and drought, they struggle to grow, they lose leaves, and simply wither. And when it happens, they don't just stop absorbing carbon, they can actually release it back and turn the system into a carbon source, which is the opposite of what we need. Sadly, this isn't a guess based on one bad summer. The team of scientists used data gathered across the Amazon for more than 3 decades. They studied how trees respond when drought hits and temperatures spike, and how the soil behaves too, because soil isn't just dirt. It's a whole living world of roots, microbes, moisture, and nutrients. When drought bakes the ground, trees don't just get thirsty. Their entire support system starts malfunctioning. The Amazon is all about the constant recycling of water. Rain falls, trees drink it. Then they release water vapor back into the air through their leaves. That process is called transpiration, which is basically the forest sweating. That tree sweat helps form clouds and bring more rain. It's like the rainforest runs its own water cycle loop. If drought weakens the trees, the loop weakens too, and then the forest becomes even drier. The last time similar climate conditions existed on our planet was around 10 million years ago. The planet and the animals living on it looked completely different back then, and ecosystems played by different rules. So, for everyone living on Earth now, these conditions are a challenge of a completely new, unknown level. What makes this feel even more intense is how scientists use drought and heat waves as a preview. They looked at how forests behave during extreme events today, because those events can act like a time machine, a quick glimpse at what normal could look like in the next 100 years. That's terrifying, because it means today's disaster seasons might be tomorrow's average weather. Like the Amazon doesn't get a bad year anymore. It gets a new baseline. And this isn't just an Amazon problem. The researchers say hypertropical forests will mostly emerge in the Amazon region. But similar conditions could also show up in parts of Africa and Asia too. When forests slip from carbon sinks to carbon sources, things will get ugly fast. It's like a feedback loop, a runaway cycle that feeds itself. The forest stops protecting the atmosphere and starts fueling the problem it used to help control. The Amazon helped keep the atmosphere stable for longer than humans have existed, and now it's getting pushed into conditions it never evolved to handle. It's not the first time, or climate type we'd better never encounter again. When Earth slammed all its land into one megacontinent, it didn't just make a bigger map, but a different planet. Pangaea created a monster monsoon system so intense it earned its own name, the Pangaean Mega Monsoon. It was like a normal monsoon blown out of proportion, feeding insane wet seasons in some regions and brutal dryness in others. It happened because one giant continent messed with winds and ocean moisture, like a giant wall in the atmosphere. This climate didn't spread rain evenly, it concentrated it. It created extreme swings, wet months that dump water like a broken fire hydrant, and dry seasons that feel like the planet forgot how to rain at all. The interior regions likely turned harsh and difficult, and coastal zones got slammed with seasonal extremes. Luckily, this climate won't come back the same way because it requires a supercontinent again. But the idea matters because it shows that Earth's climate doesn't just change from temperature, but also from layout. Rearrange continents and the whole sky starts behaving differently. During the snowball Earth period, the entire planet looked like Antarctica. Ice was stretching almost everywhere, possibly all the way to the equator. Ancient glacial deposits scientists found in places that used to sit near the tropics prove it was real. Here's the terrifying part. Once ice spreads far enough, it starts cheating. Ice reflects sunlight like a giant mirror, so Earth absorbs less heat, cools even more, forms even more ice, and the freeze feeds itself. And when all that ice melted under volcanoes released enough carbon dioxide, it likely did it violently, with extreme weather and huge chemical shifts in the oceans. Then there was the hothouse Earth that felt like the thermostat stuck on broil. There were long periods when global temperatures stayed way warmer than today. Sea levels rose and the planet's climate system behaved like it had too much momentum to slow down. In a hothouse world, the ocean expanded as it warmed, as warm water takes up more space. Ice sheets shrank, and without its natural light mirror, Earth absorbed more heat and dug itself deeper into the hot zone. Warm conditions messed with rainfall patterns and turned some regions into non-stop flood zones, while others dried into permanent drought. We should all be happy the next horrible climate scenario, anoxic events, have not happened for millions of years. But they did happen many times in the past, and may have contributed to mass extinctions. The ocean looked normal from above, but underneath, huge regions turned into low oxygen zones. Part of the ocean became stratified, meaning the layers stopped mixing properly. Warm surface water stayed on top, deeper water got cut off, and oxygen stopped refreshing the depths. Then bacteria took over, breaking down organic matter in ways that created nasty chemical conditions. Whole ecosystems collapsed, and it didn't take a meteor to trigger it. Just the wrong combo of warming, nutrient overload, and messed up ocean circulation. These events also left behind black, organic-rich sediments, like the ocean wrote down the disaster in dark ink. And the creepiest part is that the ocean anoxic events didn't feel like a dramatic explosion. They felt like a slow suffocation of the sea. After you learn about all these, some climate models from the past don't sound that scary after all. The Carboniferous Earth looked like it got trapped in wet mode. Giant swamps stretched across continents, and forests soaked the world like a sponge that never dried out. The air carried more oxygen than today, which sounds nice until you remember what oxygen does to insects. This was the era that produced giant creepy crawly legends like millipedes the size of a car. This climate also allowed to building huge coal deposits because withered plants piled up faster than nature could break them down. So, the climate didn't just create scary life, but also fuel for the future. Coal formed because the planet had endless swamp forests and the right conditions to bury carbon instead of recycling it. This climate won't come back because Earth's continents, ecosystems, and carbon cycle don't run the same way now. During the early Eocene period, our planet ran warm enough that the poles didn't freeze the way they do now, and the temperature gap between the equator and the Arctic shrank. Scientists call this an equable climate, which means Earth felt more evenly warm across latitudes. High-latitude land stayed above freezing year-round in some models and evidence. Places near the Arctic were living without deep winter ice dominating everything. It didn't mean the whole world felt like Hawaii, but it did mean fewer extreme contrasts. If the planet warms enough, pole to equator differences can shrink again, and seasons can soften in certain regions. But the Earth system today has ice sheets, ocean patterns, and human-built infrastructure that never existed back then. So if low-season Earth returns, it won't feel calm. Stop for a second and look at the ground beneath your feet. Is it a quiet suburban street, a flat basketball court, or maybe a peaceful stretch of farmland? You probably feel safe because there isn't a giant smoking mountain on the horizon, but that safety is an illusion. Yeah, sure. Yellowstone, Vesuvius, or Mount Fuji, those are the celebrities of the geological world. Giants that dominate the skyline and sometimes blow their tops. But what about a hidden threat? One that doesn't look like a volcano at all. It's invisible, it's silent, and thousands of these traps are scattered across the planet, lurking right under the foundations of our biggest cities. Scientists call them monogenetic volcanic fields. To the untrained eye, they don't look like volcanoes at all. They disguise themselves as innocent hills, flat plains, or just lovely lakes. For decades, they were mainly ignored because of their small size. But new data suggests these hidden systems are far more dangerous than previously thought. And unlike the big giants that give weeks of warning rumbles, these invisible volcanoes specialize in surprise attacks. Hold tight. To understand the danger, we have to look at the plumbing. A standard volcano acts like a simple chimney. There is a central magma chamber and a main pipe leading to the surface. Eruption after eruption, lava flows out the same vent, building a massive cone over thousands of years. Monogenetic fields break all these rules. They don't build mountains. They don't reuse the same pipe. Instead of a chimney, imagine a cracked windshield. Magma deep underground scans for any weakness in the crust over a massive area. It pushes up, cracks the surface, erupts once, usually violently, and then calms down forever. The next time magma rises, it won't use that old vent. It will find a new crack 5 miles away, or 10. This means you can't just monitor one specific mountain. The entire region is a danger zone. And because each volcano is a one-and-done event, the landscape is deceptive. You could drive past the site of a violent ancient explosion every day on your way to work and simply see a grassy knoll. The scary part is the speed. In these fields, magma can rocket from 30 miles down to the surface in less than 24 hours. It moves at a speed of up to 4 miles per hour. That sounds slow for a car, but for melting rocks, that is the speed of an elevator. This isn't just a theoretical problem for empty deserts. Take Auckland, New Zealand. It's a stunning modern city with beautiful harbors and over 1 million residents. But Auckland is built directly on top of a geological minefield. Sounds a bit crazy, right? Beneath rugby stadiums, parks, and busy intersections lies the Auckland volcanic field. Those scenic green hills scattered across the city aren't just landscaping. They're the remains of over 53 separate volcanic eruptions. Rangitoto Island, which sits just offshore, emerged from the ocean only 600 years ago. In geological time, that was 5 minutes ago. For years, this field was considered sleepy, but recently, scientists have started noticing subtle changes. The terrifying reality of a field like this isn't that a volcano we already know will erupt again. It's that a new one can pop up and go from zero to a disaster in the blink of an eye. A bubble of magma could rise silently beneath a factory, a highway interchange, or a residential neighborhood. There is no designated safe zone because the threat is spread across the entire city map. History gives us a brutal example of how fast this happens. In 1943, a farmer named Dionisio Pulido was plowing his cornfield in Mexico, on the outskirts of Mexico City. It was a normal Tuesday. Suddenly, the ground cracked open right in front of him. Smoke hissed out, smelling of rotten eggs. Within 24 hours, that small crack in a flat field had transformed into a raging volcano 160 feet tall. Within a week, it stood 500 feet high. This was the birth of Paricutin. It wiped out 2 entire towns, leaving only the stone steeple of a church poking out of the hardened lava, a haunting monument that still stands today. This geological nightmare started in a simple cornfield, and it wasn't an isolated incident. Look at the Harat Rahat field in Saudi Arabia. In 1256, a massive fissure opened up near the city of Medina. It spewed lava for 52 days, creating a river of fire 14 miles long. Today, that same volcanic field is still there, and modern Medina has expanded right on top of the ancient lava flows. Now, apply that same story to a suburb of Los Angeles, a district in Tokyo, or a neighborhood in Europe. In a matter of days, an entire city can be buried under ash. The risk is global, ranging from over 1,800 vents in the American Southwest to the restless Eifel region in Germany and similar fields in China. Experts warn that the real risk here isn't size, but frequency and location. These volcanoes tend to be explosive. When magma rises rapidly and hits groundwater, which is common under cities and fertile farmland, it flashes into steam. This creates a phreatomagnetic explosion. Instead of a slow, oozing river of lava that people can walk away from, the ground acts like a shotgun blast. It sends a massive column of ash and rock shooting into the atmosphere. In our modern world, this is a recipe for chaos. We rely on delicate systems, air travel, GPS signals, just-in-time supply chains. You don't need a supervolcano to crash the global economy. A small eruption near a major logistics hub is enough. Remember the 2010 eruption in Iceland? That wasn't even a big explosion by historical standards. Yet, the ash cloud grounded over 100,000 flights, and 10 million passengers were stranded. Volcanic ash melts inside jet engines, while toxic dust poisons crops and contaminates water reservoirs with heavy metals. It creates a domino effect. One small eruption in the wrong place triggers a cascading failure of global infrastructure. And the most alarming part is that the signals are already there. Recent geological studies have shown an uptick in activity in these distributed fields. It isn't always violent earthquakes. Often, it's bradyseism, the slow rhythmic breathing of the ground. We mentioned the Eifel region of Germany, where GPS data shows the land is rising by about 0.04 inches per year. It sounds tiny, but for geologists, that is a proper red flag. Scientists are detecting slight swells in the Earth's crust and weird spikes in carbon dioxide emissions in places that should be quiet. Magma is moving, but because these systems are so spread out, monitoring them is a nightmare. We have sensors all over Yellowstone. We watch Vesuvius 24/7, but almost no one is watching a random patch of desert in Arizona or a forest floor in Germany. These invisible volcanoes are poorly studied. We lack the baseline data to know if a tremor is just a truck driving by or the start of a Pericotine-style event. This lack of data means that when an eruption starts, authorities might have almost zero warning. In a polygenetic volcano, the mountain swells for months. In a monogenetic field, magma can shoot from the deep mantle to the surface in hours. By the time the evacuation order is written, the lava could already be breaking through the pavement. It isn't that hard to imagine the logistical nightmare. A city not known for volcanoes suddenly receives an alert. A vent is forming downtown. It sounds impossible. People delay leaving. They grab their phones to film the smoke. Then, explosions start. The ash creates a blackout. Power grids fail as wet ash shorts out transformers. Roads gridlock instantly. This scenario isn't science fiction. It's exactly what hazard models predict for places like the Auckland Volcanic Field or parts of the Trans-Mexican Volcanic Belt. We are building denser and denser cities on top of geological landmines. This doesn't mean we need to start digging bunkers, but it does require a shift in perspective. We have spent so much time worrying about the celebrity volcanoes that we forgot about the quiet ones. The Earth is a living, shifting engine that doesn't care about property lines or city limits. Scientists are now pushing for better monitoring networks, using satellites to track even the tiniest ground deformation in these boring, flat fields. Because the only way to survive a surprise attack is to see it coming before the ground cracks open. Peace and quiet on the surface doesn't always mean peace and quiet underneath. The Earth has plenty of secrets left, and some of them are just waiting for the right moment to surface. It's 3 a.m. Suddenly, a radio telescope beeps. The monitor shows a violent, massive burst of energy where it shouldn't be. The scientist spills his coffee, scrambles to hit record, and zooms in on the source, but finds nothing. Just silence. Was this a glitch or some cosmic coincidence? Actually, new research argues that this is exactly what first contact might look like. Science fiction has been preparing us for meeting ETs for decades. Since we can't travel through space yet, we kind of hope they'll come to us. Hopefully in peace without the laser weapons. But astronomers shrug and say this is highly unlikely. So they've built better telescopes and asked a better question. If life exists out there, what would actually jump out on our screens? That brings us to the streetlight effect. It's the simple idea of searching for your lost keys under the lamppost, just because that's where it's easiest to see. Scientists do the same thing with the universe. They catch the stuff that's easiest to detect, not what's most common. This is how the first planets outside our solar system were discovered in 1992. For years, astronomers stared at sun-like stars, hunting for Earth-like planets, and found nothing. Instead, the first exoplanets showed up orbiting a pulsar. When a giant star runs out of fuel, its core gets squeezed into an incredibly dense chunk of matter that spins unbelievably fast. When rotating, it can aim a radio beam our way like a space lighthouse. Every time the beam crosses Earth, we detect it like a pulse. Thump, thump, thump. That's why it got the name pulsar. Turns out it was just spinning, but we kept the name. The timing of pulses stays so precise that it works like a cosmic stopwatch. So when a nearby planet tugs on a pulsar, that perfect timing wobbles. The pulses might arrive a bit too early or a bit too late. That's how astronomers found the surrounding planets. That's the streetlight effect on a cosmic scale. The idea is that we will only notice intelligent life if it does something loud that sets off alarms or breaks some rules. A Columbia astrophysicist named David Kipping gave the idea a name, the eschaton hypothesis. Eschaton comes from Greek and points to the end, like the final chapter. The idea is that when we finally find signs of intelligent life out there, it probably won't be during peaceful times. It will be because something went wrong. Some one-of-a-kind situation for them. A moment so loud it rips through the background static of the universe and reaches all the way over here. Calm civilizations don't show up on radar. A world that runs on clean energy and keeps its tech quiet could last 1,000,000 years, and we'd never know it was there. But what if they did something big and messy just to survive? Maybe they fired up a planet-wide laser array to nudge an incoming asteroid off course. Or maybe they're testing some super advanced technology. Whatever the noise, even if it lasts for just a few seconds, it could hit radio dishes across the galaxy like a flare. Yes, all of that sounds like science fiction, but that's exactly why we'd notice it. But here's an interesting question. Have we already detected such a signal? There is one candidate that fits this profile perfectly. It remains the most famous unsolved mystery in the history of the search for extraterrestrial intelligence. In 1977, Ohio's Big Ear Telescope caught a radio surge about 30 times stronger than the background, and a volunteer spotted it in the printout. He highlighted the signal's intensity reading, 6EQUJ5, and scribbled down "Wow" next to it, which is how the event got its popular name. The signal lasted exactly 72 seconds. This duration is significant because it matched the time it took for the Earth's rotation to scan across that specific point in the sky. The signal didn't fade away. The telescope simply looked past it. However, when astronomers returned to that spot, nothing was there. They've listened for nearly 50 years, but the signal never repeated. In the science world, things that can't be repeated usually get tossed aside as mistakes. It's important to be careful because false alarms happen pretty often. There's a famous false alarm that still makes astronomers cringe. At the Parkes Observatory in Australia, telescopes kept picking up weird, chirpy signals starting in the late 90s. For 17 years, nobody could figure them out. People blamed lightning, space weather, and space invaders. But in 2015, they all figured it out. The strange signal was coming from the microwave in the break room. If a hungry scientist pulled the door open before the timer hit 0, it leaked a tiny burst of radio waves that looked exactly like a signal from deep space. 17 years of mystery for a disappointing reveal. But the WOW signal didn't behave like that. It didn't look like a satellite, a plane, or any kind of interference, and they definitely made sure it wasn't a kitchen appliance. It came from deep space, near the constellation of Sagittarius. If we apply Kipping's eschaton theory, this might be what we need to prove life outside our planet. The WOW signal could have been an engine flare from a colony ship trying to escape a disappearing world. Or it could have been a rare natural radio event that just happened to hit us at the perfect moment. The WOW signal grabbed attention because it reached us in radio waves. But Kipping's theory also asks, what if a civilization gives itself away in a completely different way, not with sound, but with pollution? Clues that technology, not nature, caused something are called technosignatures. Think of them as leftover traces. If you walk into a house that smells of fresh paint, you can assume someone was there recently. Astronomers use the same logic with planets. They scan distant exoplanet atmospheres for chemicals that shouldn't exist naturally. The biggest target is a family of chemicals called CFCs. For decades, humans filled the air with these gases because they were cheap and useful. We used them in spray cans and cooling systems, until scientists realized they were bad for the ozone layer. That's why CFCs are such a big deal. Nature doesn't make them. These chemicals are 100% artificial. So if we point a telescope at a distant planet and find its air is full of CFCs, it would be the vital clue astronomers have been waiting for. It could mean someone intelligent is down there, and they're polluting their world on an industrial scale. Besides radio waves and chemistry, you might be able to spot a civilization if they're doing something cool with light. In 2015, astronomers watching a star about 1,400 light-years away, nicknamed Tabby Star, noticed something that seemed impossible. When a Jupiter-sized planet crosses a star, it blocks about 1% of the light. But this star suddenly dimmed by 22%, and it wasn't one clean dip either. The brightness kept plunging in weird, uneven chunks with no tidy, repeatable schedule. that's something huge getting in the way. For a brief moment, scientists hoped for a Dyson swarm. That's a hypothetical megastructure made of solar panels and wrapped around a star to capture its energy. Sadly, later studies leaned toward dust clouds instead, but Tabby's star still grabs attention. We keep asking, where is everybody? But for decades, we could only watch a tiny slice of the sky at a time. That's about to change with telescopes like the Rubin Observatory that will sweep the entire southern sky every few nights, over and over, like a giant security camera for the universe. If something flickers, flashes, or suddenly vanishes, we won't just get one blurry screenshot, we'll have the replay. Finally, what if we are the loud ones? We tend to think Earth is noisy because of our TV shows and music, but those signals fade fast. Our real scream is planetary radar. We blast massive radio beams into space to map asteroids. Some researchers estimate that these shouts could be detected from as far as 12,000 light-years away. That's very far. But in space terms, it isn't even the backyard. If we really want to get someone's attention, we need to get way louder.
So, what do you like to listen to? Music? Podcasts? Maybe the sound of rain or the crackling of a campfire. But what about listening to the ocean? Not the familiar crash of waves on the shore, but sounds captured deep on the cold ocean floor. Sounds that send chills down your spine. Sounds of something big, dark, and possibly alive. And the most unsettling part is this. The true nature of some of these sounds remains a complete mystery to this day. In 1997, something strange echoed through the Pacific Ocean. Deep beneath the surface, far off the coast of South America, a sound appeared so powerful that it instantly unsettled scientists. It was ultra-low in frequency, massively loud, and unlike anything recorded before. The signal was later given a simple name: the bloop. At first glance, the bloop sounds harmless, almost playful, but what it represented was anything but. It was so intense that it could be detected by sensors nearly 3,000 miles away. Imagine standing in New York and hearing something happening in Los Angeles. Now imagine that noise traveled through deep ocean water, terrifying marine life and oceanographers. Whatever produced it had to be enormous. The signal carried patterns that felt like its source was some living creature. Whales were the first suspects, but even the blue whale, the largest animal in the world, simply couldn't generate a sound that loud. The numbers didn't add up, and that's when speculation took over. If something could produce the bloop, it would have to be larger than anything swimming in today's oceans. People began imagining creatures of impossible size, ancient sea monsters, the kraken. Some even whispered about the megalodon, a prehistoric giant shark thought to have gone extinct millions of years ago, and featured in dozens of videos right here on the bright side. The mystery only grew deeper when scientists mapped the approximate location of the sound's origin. It came from a region close to Point Nemo, the most remote place on Earth. This spot in the Pacific Ocean lies more than 1,000 miles away from the nearest land in every direction. It's so isolated that it's often called the oceanic pole of inaccessibility. Point Nemo is a place few humans will ever see. Because of its remoteness, it has become a kind of graveyard for defunct satellites and space debris. When spacecraft are decommissioned, they are often guided to fall into these waters. It's quiet, empty, almost untouched, and yet something powerful had screamed from nearby. For fans of cosmic horror, this detail felt oddly familiar. In the fictional universe of writer H.P. Lovecraft, the ancient sunken city of R'lyeh lies beneath the ocean near this very region. According to the stories, R'lyeh is where the monstrous entity Cthulhu sleeps. It's a powerful, scary, intelligent creature lying dormant for thousands of years, ready to awaken and bring about the end of the world. Of course, Cthulhu is pure fiction. Lovecraft never claimed otherwise. But once the internet made the connection, the idea took on a life of its own. But science eventually caught up. The bloop recording is still easy to find online. You can listen to it yourself. But it sounds so innocuous that you'll probably be disappointed. And today, we know with certainty that it didn't come from a living creature. Researchers later confirmed that the sound was produced by ice, specifically by an ice quake. Now, ice quakes occur when enormous icebergs fracture, crack, and break away from glaciers. When this happens, they release tremendous amounts of energy, generating ultra-low frequency sounds that can travel across entire ocean basins. These sounds are similar to biological calls, especially when recorded from far away and distorted by water. In fact, scientists compared the bloop to other known icequake recordings and found striking similarities. The source wasn't a monster. It was Antarctica itself during shifting, breaking, and reshaping. For many people, this idea brought mixed emotions. On forums like Reddit, some openly admitted they preferred the idea of a giant unknown life form. Yup. Another strange sound was captured in the early 1980s, deep in the South Pacific, during a scientific expedition near New Zealand. Researchers were exploring the South Fiji Basin, where the ocean floor lies more than 2.5 miles beneath the surface. There were short, sharp, repeating noises echoing through the water. 4 distinct bursts, each one sounding uncannily like a duck's quack. So, researchers called it the bioduck. The sound was rhythmic and consistent. Eventually, the team concluded that the source had to be biological, but identifying exactly what made the sound proved impossible. After sharing the data with colleagues in Australia, did they realize something even stranger? Similar sounds had been recorded in other parts of New Zealand and Australian waters. Decades later, the mystery remains unsolved. Some scientists believe the quacks may not be random at all. They could be a form of communication. Perhaps the sounds may come from Antarctic minke whales, though no direct proof exists. Scientists also noticed that there were several sources of sounds, and when one source spoke, the others fell silent, as if they were listening. It may have been a conversation echoing through the deep, in a language we still don't understand. Imagine a terrifying alarm blaring inside a secret laboratory, announcing that a monster from another planet has broken free. It's an ugly sound, loud, piercing, and oppressive, the kind that makes your skin crawl. In August of 1991, scientists recorded something eerily similar. Not in a lab, but deep beneath the Pacific Ocean. Across vast areas of the ocean, a strange, repeating signal began to appear at different times. It consisted of narrow, rising tones that lasted several seconds each. Researchers named this sound upsweep. It's detected most often during the spring and fall, leading scientists to believe it may be connected to seasonal environmental changes or changes in the source itself. But what exactly was producing it? No one knows for sure. The only thing scientists can say with confidence is that upsweep appeared near areas of suspected volcanic activity. But if this sound is natural, why does it seem so precise? So consistent? It almost feels artificial, as if a secret underwater facility is periodically broadcasting a distress signal from the depths of the ocean. Since its discovery in 1991, the upsweep signal has gradually weakened, making it one of the strangest and most unexplained phenomena ever recorded beneath the ocean. Now, there's another mysterious sound known simply as slow down. True to its name, this signal steadily decreases in frequency over 7 minutes before fading into complete silence. It was recorded in May 1997 on a hydrophone array located in the eastern equatorial Pacific Ocean. At first, slow down doesn't seem especially loud. But here's the chilling part. It was picked up by 3 separate sensors placed nearly 3,100 miles apart. Imagine how deafening and terrifying it was near the source itself. So, what caused it? The most widely accepted theory suggests that a massive drifting iceberg slowly came to a stop and ran aground. The idea is surprisingly plausible. A colossal block of ice is scraping along the seafloor, grinding forward until it finally halts. The location supports this theory as well, since the sound originated near shallow waters and small islands. Because of this, many scientists classify slow down alongside the bloop as a cryogenic noise caused by ice. Still, it remains just a theory. Officially, the sound has never been identified. And there's yet another eerie recording from the ocean. This one sounds like a moan, but scientists named it whistle. Go figure. It was recorded in 1997 and gives the unsettling impression that something enormous is sitting on the ocean floor and whistling. Researchers believe that something could be an underwater volcano. When they compared the whistle signal to previously recorded volcanic sounds from the Eastern Pacific, they found them very similar to each other. Most likely, all these sounds are of a natural source, volcanic eruption or iceberg collision. But it's still pretty scary to hear something like this while driving. It would be especially unpleasant to be directly above an erupting underwater volcano. Well, yeah.
Tiny microbes, basically ancient germs, have been frozen in Arctic ice for tens of thousands of years, just chilling there, since woolly mammoths were still walking around. And now, scientists think these little guys might wake up again if Arctic summers keep getting longer and warmer. Yep, you heard right. Zombie microbes. Great. These microbes have been stuck in permafrost, which is soil and ice that stays frozen solid year-round. The top layer melts a bit in the summer, but the really old stuff, those Ice Age microbes, are buried way deeper. They only thaw if things get really warm for months, not just a hot day or two. To study these microbes, the team went down to the Permafrost Research Tunnel near Fairbanks in Alaska, a long underground hallway 50 feet below the surface, carved right into the ancient frozen ground. The tunnel stretches over 350 feet and lets scientists literally walk through thousands of years of frozen history. By the way, while checking out the walls, the researchers also spotted bones of mammoths and bison sticking out of the ice. One of the reasons why the researchers went to Alaska was to see how fast these ancient microbes could come back to life. Well, they were in for a surprise. These microbes don't need years, centuries, or magic spells to wake up. Just a couple of months of warm weather. Once they're awake, they start doing their microbe stuff, which includes pumping out greenhouse gases like CO2 and methane. And that's bad news, because those gases warm the planet even more. This melts more permafrost, which wakes up more microbes, which releases more gas. You get it. Basically, it's a nasty climate loop. Anyway, when scientists went down into the frozen tunnel to grab chunks of super old permafrost, the first thing they noticed was the awful smell. It wasn't just the stench of an old basement. It was something has been frozen for thousands of years and is finally waking up bad. Weirdly, microbiologists were happy. Such a smell is actually a good sign for them because it usually means tiny creatures, microbes, are still around. Back in the lab, the team soaked the frozen samples in the water that had a special kind of heavy hydrogen inside it. This helped them track what the microbes were doing later. Then they put the samples into fridges at 3 different temperatures: cold, kinda cold, and not too cold, to copy what future Arctic summers might feel like if the warming continues. For the first month, almost nothing happened. Even the warmer samples barely changed. Only a tiny number of microbes started waking up. Basically, a microscopic trickle of activity. But a few months later, things got more exciting. Thanks to the heavy water, scientists could watch how much of it the microbes used to build their cell membranes. It helped them figure out that the old microbes were making special fatty molecules that might help them stay alive in freezing conditions. By the 6-month mark, the samples that were stored at the warmer temperatures had transformed completely. They became more active and started forming little slime layers. The scientists could actually see these layers even without a microscope. The whole community of microbes wasn't super diverse, but those that were active behaved just like modern microbes that live in unfrozen soil today. In short, those ancient microbes were definitely alive and got pretty energetic once the temperatures were warm enough. This matters a lot for the Arctic and for the whole planet because these microbes survive by eating old organic material trapped in the permafrost. When they eat, they release greenhouse gases like carbon dioxide and methane, and the Arctic is warming faster than any other part of Earth. It means that the deep frozen layers might stay warm long enough for huge numbers of ancient microbes to wake up and start pumping out gas. Right now, northern permafrost holds about twice as much carbon as the entire atmosphere. If a lot of that carbon gets released, it could speed up the warming of our planet. It can lead to dramatic consequences, setting off a whole chain of huge changes and affecting basically everything on Earth. Extreme weather will start happening more often. Stronger hurricanes, heavier rainstorms, longer heat waves, bigger wildfires. The oceans will rise too, which can flood coastlines and put towns and cities at risk. Animals, plants, and entire ecosystems can get thrown out of balance, with some species struggling to survive and food chains breaking down. People all over the world will have to deal with crop failures, water shortages, and damaged homes or infrastructure. Let's get back to our zombie microbes. The thing is, the study only looked at them in one place in Alaska, but there's a massive amount of permafrost all over the world, in Alaska, Canada, Siberia, and many other places. And microbes in different regions might behave differently as things warm up. Scientists still have tons of work to do to figure out what's coming next. I bet you're questioning yourself. Could ancient viruses infect us? Well, most of the ancient microbes frozen in permafrost are totally harmless. They're like old bacteria that only care about messing with other tiny organisms in the dirt. But scientists worry that a few of these frozen germs might be the kind that can infect people, animals, or plants. And if that happened, our bodies probably wouldn't recognize them at all, because they've been frozen since mammoths existed. Basically, there's no immune system cheat codes for us. The risks of this happening grow for a number of reasons. For one thing, the Arctic is warming almost 4 times faster than the rest of the planet. Longer summers plus hotter temperatures mean more permafrost melting. So, more ancient stuff is waking up. Plus, people might start digging more around there. Companies will mine more, drill for oil, and ships can travel new routes. All this activity tears open ground that used to stay frozen solid. This increases the chance that someone or something comes across some ancient germ that just woke up. What would actually happen then? We might run into different zoonotic diseases, basically germs that jump from animals to humans. This already happened once. Thawed reindeer carcasses released anthrax, a rare and serious illness which then infected people and animals. Luckily, we do know how to treat anthrax. But what if something even older wakes up? Besides, our immune system might have zero defense. If a virus hasn't been around for tens of thousands of years, humans today would be like, what is that thing? No antibodies, no memories of it, nothing. But the scariest part is that we don't know what's hiding down there. Scientists think permafrost might be storing trillions of frozen microbes, many of which we've never seen before. Some might be boring, and some might be super dangerous. So what if one such virus finally thawed out? The world would be dealing with a disaster no one has ever seen before. This wouldn't look like a normal outbreak. It would feel more like something out of a horror movie. First, the virus would be totally new and our immune systems definitely wouldn't recognize it. That means the virus would spread crazy fast, jumping from person to person. No one would know what to expect. It could cause weird illnesses, sudden fevers, or even something way more dangerous. Stuff as scary as the diseases people faced in old times. Scientists digging in permafrost already look for traces of those ancient diseases, so it's not impossible. Once it escapes, the virus wouldn't stay local for long. With people traveling everywhere and companies rushing into the warming Arctic for mining and shipping, the infection could go from one small Arctic village to major cities all over the world within days. Hospitals would fill up instantly and doctors and nurses would run out of supplies. Businesses would shut down. Food supplies could crash if the virus hit farm animals or crops. Shipping and travel could freeze completely. Fear and panic would spread around the globe almost as fast as the virus itself. There'd be no vaccine and no cure, because no one has ever seen this virus before. Scientists would have to start from zero. In short, a zombie virus outbreak would be totally unpredictable, and the modern world is certainly not ready for it. Did you know that over the past year, around 150 asteroids whizzed closer to Earth than the Moon? But that's not the scary part. It's that some were only noticed after they flew by. And if even one of those had taken a slightly different path, whole cities would be gone. That's what keeps the scientists worried. The invisible stuff, hiding where our telescopes can't see. Let's explore what that means. Astronomers keep a list of asteroids that wander into our neighborhood. If a rock's orbit comes close to Earth, it joins a special club we call Near-Earth Objects, or NEOs. That list can include anything from a harmless little space pebble that wouldn't break a window to a rock big enough to cause an earth-shattering kaboom. NEOs are leftover materials from when the planets were forming. Some of that rubble ended up tucked safely in the asteroid belt between Mars and Jupiter, but some pieces got nudged onto paths that cut across Earth's orbit. Those are the ones we care about, because they're still wandering around today, looping around the sun, and every now and then passing uncomfortably close to us. The biggest objects are the easiest to locate. They are rare and bright enough that they stand out in sky surveys. So far, none of those big ones seem to be heading our way anytime soon. However, the real anxiety comes from the middle class of asteroids. On paper, many of them sit in the potentially hazardous object category, or PHOs, but the nickname City Destroyer explains them better. These rocks aren't huge enough to wipe out the planet, but they could flatten a city and mess with the climate for a few seasons. Some are as wide as a football stadium and hit the atmosphere faster than a speeding projectile. NASA estimates there are around 25,000 near-Earth asteroids at least 460 feet wide, but we've only discovered a fraction of them. Basically, we have solid orbits for less than half of the City Destroyer crowd. The rest only exist as numbers in simulations. We know they should be out there. We just haven't seen them yet. Why are they so hard to spot? Some asteroids are nearly coal black, blending into the cosmic night. Others hang out close to the sun from our perspective, so our telescopes get overwhelmed by brightness. It's like trying to locate a mosquito while staring directly at the sunlight. Please don't do this. From Earth, these rocks are mostly lost in the sun's glare. We only catch a glimpse just after sunset or right before sunrise. And that chance only exists if the sky is perfectly clear and the asteroid happens to be in exactly the right spot. If not, it slips back into the sun's blind spot, playing hide and seek with us. We were caught by surprise quite recently. In 2013, the Chelyabinsk meteor came from the direction of the rising sun. No one saw it in time because it was coming from the wrong direction. It exploded high above the region, shattering windows across the city and sent more than 1,000 people to the hospital. The scariest part is that the meteor was only about 60 feet wide. Now imagine a city destroyer coming from that same direction. A stadium-sized rock stepping out of the sun's glare would give us very little warning, maybe a few days or a week instead of decades. And we know that the blind zone is not empty. Observations have already revealed at least one large asteroid in that region that scientists can seriously consider a planet destroyer. It's called 2022 AP7, and it's huge. This thing is more than half a mile wide, big enough that if it ever hit Earth, it would be a catastrophic day for everyone. Astronomers found it by using the super-sensitive dark energy camera during twilight, pointing the telescope at the region of the sky most surveys normally avoided. The good news is that AP7 isn't headed straight for Earth. Its orbit crosses the orbit of our planet, but the timing doesn't line up, so we won't encounter it this pass, the next one, or even for several centuries. The bad news is what that discovery hints at. If it took this much effort to notice something like this, what else are we missing? And 2022 AP7 is just one PHO. Other asteroids closer to the Sun were also spotted during those same twilight searches. New simulations say some of those hidden rocks are not random. A bunch of them seem to share an orbit with Venus. They do not orbit Venus itself. They orbit the Sun in almost the same lane, sometimes a bit ahead of the planet, sometimes a bit behind, like kids jogging on the same track but spread out along the lap. Astronomers already know about roughly 20 of those Venus co-orbitals, and their paths are anything but stable. Gravity from Venus, Earth, and other planets keep tugging on them, and over thousands of years, those poles could stretch their paths until they start crossing Earth's orbit. Most flybys are harmless, but one unlucky pass could be the one that counts. So what can we do about this? The first step is simple in theory. Find them earlier. The goal for astronomers is to launch infrared telescopes and get them into space. While we do have amazing telescopes like JWST or the Hubble Space Telescope, they're never pointed at the Sun, as the brightness of our star can damage them. That's why we need a telescope in orbit around Venus, or one that travels along with it. It would be in a much better spot to keep an eye on the asteroids that hang out there. NASA is launching the NEO Surveyor project that aims to solve the problem. It should scan the inner solar system to spot dangerous asteroids in time. Also, we're learning that we can actually move asteroids. NASA's DART mission rammed a small spacecraft into a rock, which affected its orbit slightly. Not by much, just enough to prove that it can be done. It's like turning a plane just 1 degree while it's still across the ocean. By the time it reaches you, that tiny change can make it miss by thousands of miles. Teams around the world spend their days babysitting space rocks, and yes, that's a real paying job. NASA has the Planetary Defense Coordination Office. Europe has the NEO Coordination Center. Observatories feed them nightly sky data, and computers immediately check each dot's orbit. If a rock might wander too close, it joins the risk list and gets extra attention. Each new photo updates the orbit a little more. Sometimes that make the danger level rise for a moment. That is exactly what happened with 2024 YR4, when it briefly reached level 3 on the Torino scale before better measurements calmed everyone down. The scale itself runs from 0 to 10, and anything that climbs above 3 is rare enough to raise eyebrows. The whole system works that way on purpose. Notice something strange, collect more data, then decide whether to relax or stay alert. Most of the job is actually pretty dull. It's a lot of number checking, orbit fixing, and crossing out false alarms. That quiet, careful routine is what lets the world respond quickly when a rock finally appears that isn't just passing by. So how worried should we be? For those huge planet-destroying rocks, the short answer is not much. Nothing that size is on the near-term schedule. Smaller city-level threats are trickier. The odds of one hitting Earth anytime soon are still tiny, but they're not zero. Think of it as a cosmic lottery that has been running for billions of years. Every once in a very long while, the universe draws a number that makes astronomers sit up and pay attention. It's not a reason to panic. It's a reason to build better eyes in space and make sure that if a bad ticket ever comes up, we see it in time to do something about it.
While
While you're watching this video, pieces of continents are slowly breaking off from below and are pulled down into the oceanic mantle, a hot, mostly solid layer that moves slowly under the seafloor. As soon as these fragments reach the mantle, they can trigger volcanic eruptions in parts of the ocean where there are no volcanoes. Plus, when continents break apart, it happens not only at the surface, but also deep down. But more on that later. This process can continue for tens of millions of years. The new study shows that Earth's insides are even more dynamic than we thought. It also explains why many volcanic islands, including Christmas Island in the Northeast Indian Ocean, contain unusually high levels of certain chemical elements. The thing is, these elements are normally only found in continental crust. Well, scientists did suspect that these elements showed up because some powerful forces deep inside the Earth took old, recycled pieces of rock and mixed them into the mantle. This process works a bit like when you mix together ingredients for cake batter. But before, researchers believed those elements came from two main sources: sediment that sank into the mantle as oceanic plates got pushed down, or from mantle plumes. Those are columns of hot rock rising up from deep inside Earth. However, these explanations don't fit all observations. In some volcanic areas, there's almost no sign that the crust has been recycled. In other places, the mantle seems to cool and too close to the surface to be affected by the rising hot rock. Scientists used to wonder how this could happen. Now we know that some of the material in those regions comes from pieces of continents that sink deep into the mantle, and these pieces affect the volcanoes that form above. The new study also suggests a curious idea. Continents don't just break apart at the surface, they peel away from below too. And this can happen over much greater distances than scientists thought before. Researchers used simulations to figure out how continents and the mantle behaved when stretched by tectonic forces. Their work is built on earlier research showing that when continents split, deep, powerful forces inside our planet create a mantle wave. This wave moves along the base of the continent at depths of about 90 to 125 miles. The wave moves extremely slowly, about a millionth of the speed of a snail, and gradually strips material from the roots of the continents. These peeled-off fragments are then carried sideways, sometimes more than 620 miles, into the oceanic mantle. Once there, they can trigger volcanic eruptions in the ocean for tens of millions of years. The research also shows that the mantle continues to feel effects of continental breakup long after the continents themselves have separated. Even after a new ocean basin forms, the mantle keeps moving, reorganizing and transporting enriched material far from where it originally came. To make this conclusion, researchers studied geochemical data from different parts of the Earth, including the Indian Ocean Seamount Province. That's a chain of volcanic formations that appeared after the supercontinent Gondwana had broken apart over 100 million years ago. Their computer models and chemical tests showed that right after the supercontinent Gondwana broke apart, a lot of magma with unusual chemicals pushed up to the surface. Over millions of years, this chemical signature slowly faded as less material came up from under the continent. The most unexpected discovery is that this happened without any help from those deep, hot columns of rock scientists used to think were needed. Now, to get an even clearer picture, let's sneak a peek into our planet's insides. Earth is about 4.6 billion years old. It was born from a huge cloud of dust and gas that slowly cooled, shrank, and hardened into the planet we know today. As it cooled, heavy metals like iron and nickel sank to the center, and lighter, rocky materials floated upward. This created the Earth's layered structure, with each layer having its own unique properties. The crust is like Earth's skin. It's our planet's outermost layer, made of solid rock. It's broken into huge pieces called tectonic plates that slowly drift over time. There are two kinds of crust:
oceanic crust, and continental crust. The oceanic crust is about 4 to 6 miles thick. It's covered with a thin layer of sediments like sand, clay, and shells. Below that are dense rocks like basalt, rich in magnesium. As for the continental crust, it's thicker than oceanic crust and is located under continents. It's made of lighter rocks than oceanic crust. Beneath the crust is the mantle. It makes up more than 75% of Earth's volume. The top of the mantle is pretty rigid, but deeper down it becomes soft and partially molten, which allows it to flow slowly. This flow is what moves the tectonic plates. At the center of the Earth lies the core. It's made mostly of iron and nickel and has two distinct layers, the outer core and the inner core. The outer core is a liquid layer of iron and nickel. It's insanely hot, up to 10,800 degrees Fahrenheit, as hot as the surface of the sun. The outer core also generates Earth's magnetic field, which protects us from harmful solar radiation. The inner core is solid because of the crushing pressure inside the planet. It's also made of iron and nickel. Now, the Earth's outer shell, called the lithosphere, is made up of the crust and the uppermost part of the mantle. It's broken into large pieces, called tectonic plates. There are a few super large plates and many smaller ones. 6 of the major plates are named after the continents they carry, like the North American, African, and Antarctic plates. But even those smaller plates play an important role. For example, the tiny Juan de Fuca plate is responsible for many of the volcanoes in the Pacific Northwest of the United States. The plates are moving like a jumble of old conveyor belts. They move very slowly, about 1 to 2 inches per year. But over millions of years, this movement shapes the face of our planet. Most earthquakes, volcanoes, and mountain building happen where plates meet, pull apart, or slide past each other. There are 3 main types of plate boundaries: convergent, when plates move toward each other; divergent, when plates move apart; and transform. That's when plates slide sideways past each other. When tectonic plates collide, the crust crumples and buckles, forming mountain ranges. About 55 million years ago, India crashed into Asia, slowly creating the Himalayas, the tallest mountains on Earth. The collision continues today, so the mountains are still rising. Mount Everest, the highest point on Earth, may even grow a tiny bit taller over time. At some convergent boundaries, an oceanic plate dives under a land plate in a process called subduction. The land above lifts up, forming mountains, and the sinking plate melts and triggers volcanic eruptions. This is how some mountains in the Andes of South America were formed. When 2 oceanic plates collide, one usually slides beneath the other, creating deep ocean trenches, like the Mariana Trench in the North Pacific, the deepest point on Earth. These collisions can also form underwater volcanoes that eventually rise above the ocean and turn into island chains, such as Japan. At divergent boundaries, tectonic plates move away from each other. In the oceans, magma from deep in the mantle rises to fill the gap. This creates underwater mountains and volcanoes along the seam. This process renews the ocean floor and slowly widens the ocean basins. By the way, a single mid-ocean ridge system connects all the world's oceans, making it the longest mountain range on Earth. On land, when plates pull apart, they form giant valleys, such as the Great Rift Valley in Africa. If this stretching continues over millions of years, East Africa could split off to become a new landmass. One famous example of transform boundaries is the San Andreas Fault in California. Unlike convergent or divergent boundaries, transform boundaries usually don't create mountains or oceans, but the grinding motion can cause powerful earthquakes, such as the 1906 earthquake that destroyed much of San Francisco. Australia feels like the safest place on Earth, geologically speaking. No megavolcanoes, no massive fault lines slicing cities in half, no constant earthquake alerts. It looks solid and unbreakable, but according to a brand new global stress map of Earth's crust, Australia is one of the most internally stressed pieces of land on the entire planet. It's not shaking or cracking yet, but it's quietly storing energy like a bent ruler about to snap. To understand why this is such a big deal, imagine Earth's crust like a giant jigsaw puzzle made of moving slabs called tectonic plates. These plates float on softer rock below and push, pull, or grind against each other. Where plates meet, earthquakes and volcanoes make sense. But stress doesn't just stay at the edges, it travels. It builds up inside plates too, like pressure spreading through frozen ice when you squeeze it. Scientists mapped over 100,000 real stress measurements from oil wells, rock tests, and earthquakes to see where Earth is being squeezed the hardest right now. When they laid all the data together, the map lit up like a warning sign, and Australia stood out. This shocked scientists because Australia sits far away from plate boundaries, which usually means stability. But instead of relaxing, the Australian continent gets squeezed from multiple directions by nearby plates, especially the Pacific and Eurasian ones. The stress doesn't release easily, so it piles up inside the crust, and then nothing moves. Until suddenly everything does. One of the strangest discoveries showed up in places like the Bowen Basin, where stress directions twist and rotate underground. That's bad news because unpredictable stress behaves like glass about to shatter. These rotating stress fields make it nearly impossible to say when or where cracks could form. It could be years away or tomorrow. And human activity makes it even riskier. Drilling deep into the crust for geothermal energy or injecting fluids underground can nudge these stressed zones just enough to trigger fault movement. This doesn't mean Australia is about to split in half next week, but it does mean the idea of geologically safe might be outdated. Scientists now think Australia could eventually fracture internally and form new fault systems where none existed before. What makes the new stress map different from older models is that it doesn't just explain past earthquakes, it helps identify future risk zones before anything breaks. Countries can use this data to decide where drilling is safer, where tunnels shouldn't go, and where infrastructure needs reinforcement. But even with all this data, we still can't predict the exact moment Earth will snap. Stress maps tell us where the tension is. They don't tell us when it gives up. But this idea of continents quietly tearing themselves apart isn't just theory. Africa gives us the clearest real-world example. It's slowly unzipping itself. So slowly that no human will ever wake up and see a new ocean where land used to be, but fast enough that scientists can actually measure it happening right now. Deep beneath East Africa, the ground stretches, thins, and pulls apart as if the continent is taking a deep breath and never fully exhaling. And over millions of years, that stretch could turn into an ocean. This whole process centers on something called the East African Rift System, or EARS for short. Think of it like a giant tear running through the continent, thousands of miles long, cutting through countries like Ethiopia, Kenya, Tanzania, and Mozambique. It's one of the biggest rift zones on Earth. A rift zone is exactly what it sounds like, a place where the planet's crust is being pulled apart instead of squeezed together. And Africa just happens to have one of the most dramatic examples anywhere on the planet. What's really happening is that Africa isn't one solid plate anymore. It's splitting into two massive chunks, the Nubian plate to the west and the Somalian plate to the east. These two plates are drifting away from each other at a speed that sounds laughable, just less than an inch per year. That's about the speed your fingernails grow. But give that process millions of years and suddenly continents don't look so permanent anymore. In 2018, photos of a giant split in Kenya went viral across the internet. Headlines screamed that Africa was splitting in half right now. It looked dramatic, but that moment didn't mean Africa suddenly broke overnight. That rupture was more like a surface ripple, a small local sign of a much bigger process that's been going on for around 25 million years. And if we could travel in time to 5 or 10 million years from now, we would probably see the crust thin enough for seawater to rush in. When or if that happens, East Africa would slowly peel away from the rest of the continent, and a brand new ocean basin would form between the two plates. Africa would lose its eastern shoulder, and maps of the world would need a serious update. As strange as that sounds, it's actually totally normal for Earth. The planet never stops reshaping itself. It just works on a timeline so slow that our brains struggle to process it. The continents we know today feel ancient and permanent, but they're basically temporary arrangements. About 138 million years ago, South America and Africa were locked together like puzzle pieces. You can still see it if you look at their coastlines. They match almost perfectly. East Africa drifting away will just be the next chapter in that story. Australia's story could follow a different path, but the physics are similar. Stress builds, rock resists, then the rock fails. And stress doesn't care about borders, cities, or how calm the surface looks. That's why scientists are so concerned about something called SH max, the direction of maximum horizontal stress. In simple terms, it tells us which way the Earth is squeezing the hardest underground. If that squeezing lines up with existing fractures, earthquakes become more likely. If it cuts across old faults, new ones can form. Turkey is another place where the stress map practically screams danger. The country sits where Arabian, Eurasian, and African tectonic plates collide. There's also a smaller Anatolian plate on which Turkey is located, and which gets squeezed westward like toothpaste, grinding against massive faults. The stress map shows SH max pointing in directions that load these faults perfectly. Now, researchers looked at ancient lava flows near one of Turkey's faults and realized they weren't random. Lava sheets once flowed smoothly across the land, cooled into solid rock, and then got pulled apart over time, like a snapped chocolate bar. That gave scientists a rare, clear snapshot of how continents deform from the inside out. To date the lava, the team used microscopic zircon crystals trapped inside it. These crystals work like natural stopwatches. They trap helium created by radioactive decay, and by measuring that helium, scientists can tell when the lava erupted and cooled. When they combine that with satellite images and remote sensing, the scientists managed to see Earth's slow-motion movements. The Tuzgolu Fault stretches more than 120 miles and is so massive that you can spot it from space. For years, scientists assumed it behaved like many of Turkey's dangerous faults, where land slides sideways past itself. But this new research flipped that idea on its head. The fault isn't sliding, it's slowly ripping open. The land on either side moves away from each other at less than an inch per year. That sounds tiny, but then again, over thousands or millions of years, that motion adds up to continents literally thinning and breaking. And since the fault sits where three massive tectonic plates meet, this matters way beyond Turkey. All this once again reminds us that continents don't just collide or slide. Sometimes they stretch until they snap. And places that look calm on the surface might already be under invisible strain, inch by inch, year after year, rewriting the map long before anyone feels the shake. Yellowstone is the internet's favorite doomsday volcano. Maybe you heard the prediction. One super eruption, then a continent dusted in ash and temperatures going down. A perfect disaster movie scenario. Yet, geologists worry about a different kind of volcano. One that won't explode only once. It could rip the ground open, flood the entire continent with lava, and make the air unbreathable. And we know this because it happened before. Right now, researchers think there might be around 20 supervolcanoes scattered across the planet. Short story, we fear those. Long story, a major supervolcanic eruption could collapse modern society as we know it. A normal volcano can cause a local disaster. It can wipe out a city and turn a region into a no-travel zone. When Mount St. Helens exploded in 1980, it was huge. The eruption blew the top off a mountain and flattened forests like knocking down dominoes. It showed the world just how scary volcanoes can be. But in geological terms, it's nowhere near what a supervolcano could do. Mount St. Helens threw out roughly a third of a cubic mile of ash. enough to make a football field pile about 150 miles high. For comparison, a supervolcano could bury the entire state of Texas 5 feet deep, and Texas stretches about 800 miles. Volcanoes like St. Helens are mountains that build up over time, layer after layer, like nature stacking spilled wax. They erupt, they cool, they erupt again, and you end up with a cone that looks cool in photos. A supervolcano is like a hidden pit. It resembles a giant underground tank of molten rock covered in a thick slab of crust. Imagine the magma chamber like a huge underground room, and the ground above it is the ceiling. During a super eruption, cracks rip open across that ground and magma forces its way up through them, like steam blasting out of a pressure cooker. Ash and gas roar high into the sky. It can start in multiple spots across a wide area, not one neat hole. The magma chamber underneath can empty so violently that the roof above it collapses, the land drops, and what's left is a massive bowl-shaped scar called a caldera. And Yellowstone is the prime example. About 631,000 years ago, Yellowstone had a massive eruption and it left behind a giant caldera about 30 by 45 miles across. Now it's a national park, but it's also basically a footprint, like a warning. If Yellowstone erupted again, the first super hot clouds of ash and gas could blast outward and burn everything nearby. Then the ash would spread. And ash is not like the fireplace dust. It hurts to breathe. It wrecks engines, and it can shut down flights and machines. Regular volcanoes mostly hit the area around them with lava. A super eruption turns the air itself into a real danger. Ash spreads far and jams the things we depend on. High up, sulfur can turn into a thin haze that will block some sunlight. That can cool things for a while and mess with growing seasons, even far from the eruption. And winds can spread that effect well beyond the US. However, geologists worry about something even worse. A kind of eruption that can keep going in waves and cover huge regions in lava. It's called a large igneous province. It's not one volcano, it's a whole stretch of crust that starts leaking lava through long cracks over and over for a long time. Instead of one giant explosion, it's more like Earth turning on a lava faucet that just keeps going. Imagine a crack in the ground hundreds of miles long. Out of that crack comes a sea of lava, but this isn't the sticky, slow stuff you see in Hawaii. This is hot, runny, fast-moving lava, and it doesn't stop. It spreads, floods low spots, stacks into layers, and then does it again. And that's what makes LIPs scarier than a supervolcano. They drag on. They can erupt in repeated pulses over hundreds of thousands to a few million years. We have scars to prove it right here in the US. About 17 million years ago, the Pacific Northwest ripped open and created the Columbia River basalt. Lava did not just coat the land, it drowned it. The total amount that erupted was around 42,000 cubic miles. That's enough to cover the whole US in lava about 58 feet deep. But how can Earth produce enough lava to bury a mountain range? It's because the planet is still churning inside. Imagine Earth like a pot of thick tomato soup sitting on a stove. Earth's core is the stove, and it's extremely hot. The soup is the mantle, a thick layer of rock that moves slowly. Now and then, a massive blob of superheated rock rises from deep in the mantle, possibly from the boundary above the core. Scientists call this a mantle plume. When it reaches the cooler crust, it spreads out, pushes upward, and when it breaks through, it does not build one neat mountain. It can open long cracks and feed eruptions in repeated bursts for a very long time. However, while lava burns everything in its way, it's not what wrecks the planet. The gas does. These eruptions release huge amounts of carbon dioxide and sulfur, and we can assume the consequences of that because it happened before, and not just once. About 252 million years ago, a massive LIP eruption began in what is now Siberia. It lines up with the worst extinction event in Earth's history, the Great Dying. Around 90% of species disappeared. Huge amounts of gas flooded the air and trapped heat. The ocean soaked up some of that gas and turned more acidic. Acid rain fell again and again. Life on Earth crashed. Scientists believe that in the last 500 million years, there have been 16 major extinctions like this, and that 15 of them line up closely with LIP timing. These geological formations changed Earth so many times, and scientists now wonder, what if Yellowstone and that massive lava flood in Oregon are actually a part of the same system? Look at Idaho from space, and you see a long, flat track across the state called the Snake River Plain. It points from the old lava flood region toward Yellowstone, like a trail. That path exists because Earth's surface moves. The outer layer is split into giant plates that slowly slide. Under Idaho and Yellowstone, a deep, hot zone keeps feeding eruptions. As the plate moves, the eruption zone shifts with it, leaving a long trail behind. That's why the rocks get older the farther you go from Yellowstone. It's the same heat source, just a moving target. And if you roll the plate's motion back far enough, that trail points closer to where the Columbia River basalts formed. That's why some geologists think the Northwest lava flood and Yellowstone could be connected parts of one long-lived system. Finally, if it's all part of one big apocalyptic system, is it time to pack the bags and flee to Mars? Will it happen again soon? Even if they share the same story, that does not mean the worst part is coming back soon. The lava flood chapter played out millions of years ago. Today, Yellowstone is simply where that deep heat shows up at the moment. And sure, it can erupt again, but the most likely eruption isn't some giant doomsday blast. It's a steam explosion, when super hot water flashes into steam and blows rock apart. Lava flows and smaller eruptions can happen too. The caldera-making nightmare is a rare one. If Yellowstone ever started building towards something big, it wouldn't be sneaky. You would see it coming. A lot more earthquakes than normal and the ground lifting faster than usual. The clearest right before signs would likely show up in the days or weeks before it. We cannot stop a planet-scale eruption. We can only watch for the warning signs and plan. But hopefully, if the planet decides to get rid of us, by the time it starts sending warnings, we'll already finish turning Mars into our new home.
Well, get this. Scientists could bring Neanderthals back to life within the next 20 years. Not as fossils, not as simulations, but as actual living beings. And no, this isn't a sci-fi movie pitch, but a real debate happening right now in genetics labs and ethics panels around the world. The DNA has already been decoded, and the only thing standing between us and a living Neanderthal is whether we should do it, not whether we can. So let's get some things clear. Neanderthals weren't cavemen dragging clubs around as cartoons taught us. They were just like humans, our close cousins, who lived across Europe and Asia for hundreds of thousands of years. They cared for injured members of their society, made tools, wore clothing, and survived scary Ice Age conditions that would wreck most modern humans. Then, around 35,000 years ago, they vanished. No one fully agrees on why. Changes in temperatures, competition with Homo sapiens, health issues, or interbreeding. All of it probably played a role. The reason this resurrection talk even exists is that scientists finished sequencing the entire Neanderthal genome back in 2010. It's like an instruction manual written in DNA, telling a body how to grow, function, and survive. Now, once you have that manual, the question shifts from what were Neanderthals like to could we rebuild one? This is where CRISPR enters the story. It's a gene editing tool that works like molecular scissors. It lets scientists cut DNA at precise spots and replace sections with different genetic code. They already use it to study health conditions, edit embryos in animals, and even modify human stem cells in labs. Now, in theory, scientists could take human stem cells and slowly replace modern human DNA with Neanderthal DNA, piece by piece. One famous geneticist from Harvard says it could happen within a couple of decades. He doesn't mean that copying a Neanderthal straight from a fossil, because ancient DNA is too damaged for that. Instead, his idea is to take human DNA and slowly change it piece by piece until it matches Neanderthal DNA. So it wouldn't be a copy from the past, but a modern human body rebuilt using Neanderthal instructions. Whoa! Scientists are willing to go through all that because they want answers to questions like why Neanderthals disappeared and we survived. How did their brains work compared to ours? Did they think differently, feel differently, or process language in unique ways? A living Neanderthal could answer questions that bones and fossils never can. Some researchers even think this could help modern medicine. Since Neanderthal genes influence immunity, metabolism, and inflammation, studying a full Neanderthal biology could reveal why certain conditions hit humans the way they do today. So, in a strange way, reviving them could help us. But all this excitement hits a wall made of ethics. A Neanderthal wouldn't just be a lab mouse, it would be a person. That single fact flips the entire project upside down. You can't treat a person like an experiment, even if science really wants answers. Being the only Neanderthal on Earth would be tough, to say the least. They'd have to live with no culture, no community, no one who would want to truly share their biology. They'd grow up surrounded by modern humans who would study them nonstop and forever label them as an experiment. So, critics of the idea are sure that kind of isolation could cause serious psychological damage. There's also the issue of consent, which the experiment would completely break. No Neanderthal can agree to being born into a modern world, raised by humans, studied for life, and used as proof of a theory. Consent is crucial in medical ethics, and you can't even test meds without it. Cloning a human ancestor would break that rule. Now, if we forget about ethics, there are also serious biological risks. No one knows how a reconstructed Neanderthal genome would behave in a modern human womb. Pregnancy alone could be dangerous. Development might not follow expectations. Immune reactions could go wrong. Even small genetic mismatches can cause massive problems when you're building a whole human from scratch, And even if everything worked out, the results might disappoint. One individual couldn't recreate Neanderthal society, and behavior comes from culture as much as DNA. Without a full population, the answers we get could be shallow, misleading, or incomplete. The debate on whether we should or should not bring back Neanderthals is so intense because the possibility of doing so is very real. Genetic engineering keeps accelerating, and the tools keep getting cheaper, faster, and more precise. Right now, no lab has approval to try this. No Neanderthal embryo exists. But scientists, ethicists, and state officials already argue about rules, limits, and red lines, which is another proof of how close it feels. It also brings up the big question of whether scientific curiosity has limits and who gets to decide them. Right now, there's no law that bans resurrecting extinct humans. Once one country allows it, others could follow, faster than the rules can keep up. And then, there are scientists who counter all this with a different argument. What if not doing it is also unethical? They point out that we already revive extinct animals, manipulate genomes, and alter life at the deepest level. Understanding Neanderthals could help modern humans survive future climate shifts or mass health disorders. If Neanderthals thrived in extreme conditions, their biology could hold survival clues we desperately need. From that perspective, if we refuse to explore this knowledge, it could cost the world many lives someday. If all this doesn't touch your heart at all because you have nothing to do with Neanderthals, here's a surprise for you. When you look in the mirror, you're probably staring at a tiny piece of one of them. It could literally be in your DNA. According to a study from a couple of years ago, Neanderthals didn't just vanish into thin air, but blended into us. Modern humans, whose ancestors migrated out of Africa, carry about 1 to 4% of Neanderthal DNA. Scientists only have a handful of high-quality Neanderthal genomes to study, just 3 really solid ones. They come from bones found in a cave in Croatia that are about 50,000 to 65,000 years old, plus 2 others from Eurasia dating to around 80,000 and 50,000 years ago. It's not a lot to work with, which means every new discovery matters a lot. Every person has 2 versions of each gene, one from mom and one from dad. When 2 very different groups mix, their offspring end up with more genetic variety. The scientists compared DNA from those 3 Neanderthals with genetic data from about 2,000 modern humans. What they found was shocking. Neanderthals themselves may have carried up to 3.7% modern human DNA. So Neanderthals weren't just mixing into us, we were mixing into them too. Roughly 1 out of every 30 Neanderthal parents may have been a modern human. And this didn't happen just once. The DNA shows at least 2 big periods of mixing. One happened around 200 to 250,000 years ago, and another around 100 to 120,000 years ago. There may have been more, but DNA is like a blurry photo. The older the event, the harder it is to see clearly. According to another recent study, most Neanderthal DNA in modern humans came from one long, intense mixing period about 47,000 years ago that lasted nearly 7,000 years. That's generations growing up together. This lines up with real bones, too. Scientists found skulls about 100,000 years old in Middle Eastern caves that look mostly like modern humans, but with thick brows and other Neanderthal-style features. Sadly, it looks like Neanderthals had a much smaller population than scientists thought. This makes it harder for them to stay genetically separate. As waves of modern humans kept moving out of Africa and mixing with them, Neanderthals didn't disappear, but dissolved into the larger human population. So, Neanderthals didn't lose the game of evolution. They're part of us. It's something worth keeping in mind when you think about the ethical side of bringing back one of them.
Something is about to reshape the entire future of the West Coast. The coastline, the infrastructure, the whole map. Scientists fear there is not 1 but 2 big earthquakes coming, one caused by another. This wasn't even on the radar for most people, but new research is changing everything. For decades, everyone treated the San Andreas Fault and the Cascadia subduction zone like 2 separate monsters that just happened to live in the same neighborhood. They were powerful, yes, but independent. But now, scientists believe these 2 giant faults are mechanically linked, and one can literally pull the other into rupturing shortly afterward. Cascadia moves, San Andreas moves. San Andreas tears, Cascadia tears. And the potential consequences of that are honestly haunting. Scientists found evidence that it happened at least 10 times in the last 3,100 years. Earthquake, pause, earthquake. It comes from marine sediment cores, which are like time capsules pulled up from the ocean floor. Researchers analyzed layer after layer of seabed sediment and found doublets, paired debris layers created by 2 massive quakes happening so close together that the ocean barely had time to settle between them. That discovery takes us to the Mendocino Triple Junction, the geological troublemaker of the West Coast. It's the place where 3 tectonic plates crash and grind into each other like badly aligned gears. It's also the zone where the San Andreas meets Cascadia, which makes it the perfect place for these double quakes to form. The stress changes caused by a rupture in one fault travel straight through this junction and destabilize the other. It's benign when it happens to a bookshelf. When you move one book, 3 others shift. But when you think about it like a coastline with millions of people, entire cities, major infrastructure, it instantly feels terrifying. To many people who live on the West Coast, the San Andreas kind of feels like a California's problem, and Cascadia like an Oregon and Washington's problem. But when you understand that these 2 faults can essentially fire at each other, it stops being a local issue and becomes a continental one. A Cascadia megaquake alone can hit magnitude 9.0 plus, rip open 600 to 700 miles of seafloor, and send a tsunami roaring toward the Pacific coast. And it could just be the first quake, and then, maybe minutes later, the San Andreas snaps in Northern California. The shaking could ripple down the state like a zipper tearing open a jacket, and if it goes the other direction, it could be just as bad. If the San Andreas ruptures first, the intense stress redistribution can destabilize the Cascadia subduction zone. You could get the California quake first with buildings rocking, highways breaking, and power stations failing. And then, soon after, the ocean pulls back in Oregon or Washington. And the 20-minute countdown to a tsunami begins, a follow-up disaster. It's the kind of chain reaction you don't want even in a video game, let alone real life. This discovery also tells us something eerie about the earthquake in 1700. The one that sent a tsunami across the Pacific so huge that it struck Japan with no warning. Japanese fishermen called that wave the orphan tsunami because it arrived without any felt shaking. Only centuries later, scientists figured out that it came from the Pacific Northwest. But until recently, no one knew that the San Andreas might have felt that event too, and it possibly slipped or destabilized because of it. So, the whole West Coast may have moved together. And we've come to the scariest part. All this isn't about if, it's strictly about when. The faults have a rhythm, a pace, and a geological heartbeat. We've seen how they behave across thousands of years. We know what they did, and now we know they sometimes do it in sequence. The real fear isn't the first quake. California already expects a big one. The real fear is the second quake, the one that comes before you've checked on your family, before emergency responders regroup, before the power comes back, and before the dust settles. Even if you don't live on the West Coast, this matters for you too. The ports in California, Oregon, and Washington handle a massive chunk of America's imports. Knock them offline, and it's not just the coastline that feels it. The ripple hits the entire country, and potentially the world. Grocery prices spike, supply chains freeze, gas availability dips, shipping timelines go nuts. The world is much more connected than any of us thought, and a geological double punch on the Pacific coast wouldn't stay a local disaster. It would spread, thread by thread, into everyone's life. So, those in power must prepare not for one giant rupture, but for two. Emergency plans, evacuation routes, response times, and power grid designs, all of it needs updating. Because nature has now shown us what even a single major rupture can do to a modern economy. It happened in Japan in 1995, on January 17th at 5:46 in the morning. The quake hit right by the northern tip of Awaji Island, only 12 miles from Kobe, a huge, busy city with about 1.4 million people back then, and another 2.6 million in Osaka nearby. The rupture ripped along the Nojima Fault for about 25 miles. That doesn't sound like much until you realize entire buildings can't survive that kind of sideways shove. More than 5,000 people lost their lives. 43,000 were injured. Nearly 400,000 buildings were irreparably damaged. This disaster hit one of Japan's largest industrial zones. And when you mess with a place like that, the shock doesn't stop at the shoreline. The damage was $200 billion US in losses, from smashed buildings and infrastructure and many businesses shutting down. Kobe's port just collapsed. Only 30% of the Osaka-Kobe railway lines worked. Part of National Route 28 literally vanished into the ground. Schools, hospitals, and municipal buildings, 85% of them took damage or were unusable. Fires broke out across Kobe, almost 300 separate incidents, burning the equivalent of 70 US city blocks and taking another 600 to 700 lives. Almost 100,000 people permanently left the region, 2.5% of the whole population gone in less than a year. And here's a detail that stuck with me. So many bridges failed that engineers suddenly had to confront how poorly older designs handled lateral shaking. Houses with heavy tiled roofs, built to fight typhoons, crumbled because all that weight sat too high. But the newer homes made after the 1981 building code revision stood. And that's when Japan realized that modern seismic standards were crucial to follow. Japan threw $58 billion US into restoring the region. Power came back in days. Roads and rail returned in 5 to 8 months. The main expressway took 21 months. The port was fully rebuilt in just over 2 years. And by then, all debris was cleared. Within 15 months, manufacturing jumped back to 98% of its old level. Stores reopened. By 1999, Kobe's economy reached roughly 75 to 90% of pre-quake levels. Japan overhauled its disaster management system entirely. They set up the Central Disaster Management Council and rewrote building codes. They upgraded everything from emergency drills to fire-resistant city layouts, and they launched the Earthquake Early Warning System that now gives Japan those precious few seconds before shaking hits. The same system that saved countless lives since 2007. But despite all this improvement, the Kansai region still sits on dangerous ground. The Roko Awajishima fault system, the same one that snapped in 1995, still runs under them. The 2018 Northern Osaka quake and the 2024 Noto Peninsula quake reminded everyone that this threat didn't disappear. It just waits its turn. A future large event on that system could hit even harder simply because the region has grown more complex, more interconnected, and more economically loaded. So Kobe wasn't even a triggered double fault rupture, but it still broke a major industrial hub, reshaped a national economy, and permanently changed global shipping routes. That's why when scientists started talking about 2 joint faults firing off back-to-back in Cascadia and San Andreas, you don't even have to imagine the consequences. We already got a preview in 1995. We've all thought about rewinding time, whether to fix that cringeworthy mistake or a sneak peek at next week's sports scores. But let's be real, those thoughts fade. For most of us, time travel is just a fun movie idea. But for astrophysicists, time travel isn't just sci-fi. It's a serious puzzle hidden in the fabric of space-time. And now, new models suggest the universe might just allow time to bend in ways that didn't seem possible. Humans were intrigued with manipulating time long before complex scientific models. In an ancient Hindu story, a king visits the heavens for minutes and returns centuries later. In a Japanese legend, a fisherman spends days in an underwater palace and comes back to find generations have passed. These are some of the myths that hint that time doesn't flow the same everywhere. And time traveling as a concept didn't just pop up from regret or curiosity, it also came from watching space. Time feels like one constant in our lives. It's always moving forward like a river. It flows forward and it's predictable. But when we zoom out, way outside of our planet, it's a different story. To physicists, time bends, stretches, and slows down depending on how fast you move or how strong the pull of gravity is. And that's not just a theory, it's measurable, proven, and built into the technology we use every day. For example, astronauts on the ISS orbit Earth at 17,000 miles per hour. And their clocks tick just a tiny bit more slowly than ours. It's only milliseconds, but technically, they've aged less. You can see this effect in your everyday GPS as well. Satellites up there feel less gravity, so their clocks tick a bit faster. Imagine playing a racing game where your car and your controller are a bit out of sync. That's why GPS needs constant tweaks, or else your phone would think you are miles away. Gravity also messes with time. Scientists proved it using 2 atomic clocks. Atomic clocks are like the ultimate devices that measure time. They don't tick with gears or crystals. They tick with atoms, the universe's own metronomes. One clock was on a skyscraper roof, the other closer to the ground. The lower one, feeling stronger gravity, ticked just a tad more slowly. The difference was tiny, but it proved that even height can tweak time. Now picture being near a black hole where minutes could equal years elsewhere. This might help you get those mind-bending scenes from Interstellar. So yes, time bends, and scientists know this. And the challenge now is learning how to do it on purpose. Einstein's work proved that time could move differently for different observers. The faster you move, the more slowly time passes for you. This phenomenon is called time dilation. Think of Marvel's comic Flash. He runs incredibly fast, but he doesn't really slow the world down. His own clock runs more slowly, so to him, everything else looks frozen. If you could reach the speed of light, your time would almost stop entirely, while the rest of the universe would keep racing ahead. For decades, physicists believed that was the only path to real time travel. But the Flash is a superhero, and Einstein proved that nothing with mass could reach that speed. The faster you go, the heavier you become, and the more energy it takes to keep accelerating. To actually reach light speed, you'd need infinite energy, because your mass would become infinite too. Since infinite energy doesn't exist in the universe, it's physically impossible. That's why physicists started asking questions like, if time can stretch and bend, could it also fold? In 1994, physicist Miguel Alcubierre posed a question. Could Einstein's math let us travel faster than light, not by breaking the rules, but by bending space itself? His answer was, maybe. He imagined a warp bubble, a region of space surrounding the ship that moves with it, carrying it along like a cosmic conveyor belt. In this bubble, the spaceship itself doesn't move. The space in front shrinks, the space behind stretches, and the ship rides the wave forward like a surfer gliding on a moving sea. Inside the bubble, the ship feels no motion. It's sitting still, but the bubble carries it across huge distances. And because the ship isn't moving through space faster than light, it doesn't break Einstein's rules. The universe itself does the moving. That hypothetical bubble would need a special kind of energy to bend space-time this way. Originally, Alcubierre's equations required negative energy or exotic matter, a substance that's never been found in usable amounts. Early estimates said we'd need more energy than Jupiter could provide. For years, scientists have wondered if the universe could allow something like a cosmic shortcut without breaking the known rules of physics. While nothing practical has been found yet, theorists have explored models that closed time-like curves, loops in spacetime that bend back on themselves. Here's how it works. Imagine spacetime as a giant sheet. Normally, moving across it takes time, like walking across a field. But a closed time-like curve is like drawing a circle on that sheet. If you walk along it, you could eventually end up back where you started. In spacetime terms, the start and end could be different moments in time. So instead of just moving through space, you're following a path that loops through time, a theoretical shortcut to the past. This isn't pressing a button to hang out with your younger self, it's more like a time detour, a loop in the universe that could let something trace its way back to the past, all without breaking the speed of light. Einstein's math already lets spacetime do gymnastics near spinning black holes, twisting like a cosmic corkscrew. Physicists can explore these loops on paper, but creating one in a lab is far beyond our reach. If one day we could turn this math into a real spaceship, a warp bubble wouldn't actually make the ship go faster than light. Well, technically, there would be no speed. Inside the bubble, the ship wouldn't move at all. Instead, it would fold space like a piece of paper, bringing two faraway points together. The ship could get there in minutes while still obeying the cosmic rules. This is how it worked in the famous Star Trek series, and what many movies adopted as a method for space travel. In a hypothetical situation, a warp bubble wouldn't just be for spaceships. You could send a probe, a package, or even a cup of coffee across the galaxy without it actually moving through space. It's pretty cool, because since the bubbles move space around it, everything inside stays totally still relative to the bubble, which means no spills and no weird forces acting on the coffee. However, we are still far away from that point. The challenges we face are pretty massive. We still don't have enough energy, and folding space-time at will is still out of our reach. But for the first time, The math suggests that it's not impossible. What used to seem like pure sci-fi is now popping up in real science journals. These concepts aren't just about whipping up time machines or warp drives. Even if we never pull off a warp drive, figuring out how space-time works is a big deal for understanding reality. For now, it's all theory and simulations, but every experiment pushes the impossible line a little further. Yesterday it was no, today it's maybe. And in science, maybe is where the most exciting things happen. So while we're not ready to build time machines or bubbles across galaxies yet, scientists can now study and test these ideas using real physics, which will lead to new exciting discoveries. That is, unless future Earthlings figure out how to do it maybe 1,000 years from now, so they travel back in time to show us how we can do it ourselves. Which will create a grandfather paradox, unless someone sends the idea back in time and creates a closed time loop.
That's it for today. So hey, if you pacified your curiosity, then give the video a like and share it with your friends. Or if you want more, just click on these videos and stay on the bright side.